Hello, Ayushman. I regret changing my name. It's fine. Hello, JBQ. Hello. Hello, everybody. We're still setting up the stream. I think I will take a bit more to join. Not long, but so we're still gearing up. I read a blog post on migrating from S3 to plus Cloudflare to a big VPS. Wait, it's not even a VPS. It's like we got physical servers, bare metal on Hetzner. How did that go? Pretty well so far. Like it works. It costs less. I think we have hit occasionally the monthly transfer bandwidth limit, but that's like not big a deal because we have proxies and the ecosystem has started incorporating the concept of proxies. Like for example, the Zig app doesn't try to download Zig from the official Zig repository directly, the original official website directly, but it tries proxies first. Same with GitHub Actions. So far so good. And the performance, it's well, obviously dramatically better. Like dramatically. You know where's Toggle? I think Toggle is sick. I'm guessing. Did I so while that is technically a possibility, sometimes streamers don't stream and they are still alive. What is the bandwidth limit? The bandwidth limit is basically that on Hetzner, there's like a limit of, I don't remember, like 3 terabytes, maybe. There's like a total amount of transfer size that you can, like of bandwidth that you can consume within a month. And when you hit that limit, then your connection is capped and you can only transfer at much lower speeds. I forget exactly how like draconian is the ETA cap, sorry, the speed cap, but it is significant. So basically your site, it doesn't become unreachable, but it does become, perceivably degraded when it comes to downloading stuff, for example. But it's fine. It's in a sense part of the plan. It basically has the nice property of placing friction where you want change to happen in the ecosystem. We want to have the concept of proxies for downloading the compiler toolchain. And so, you can go and tell people, you should do this and you should do that. And sometimes it works. But you know what works even better? Having a system where who owns the proxies? There's a few different community members. Just for clarity, the reason why you can trust the proxy is because we sign all the tarballs. So the tooling that downloads those tarballs from proxies, be it GitHub Actions or ZigUp or ZVM or any other tool of that kind, they check the signature. So at the end of the day, it doesn't even matter who owns the proxies from that perspective. But there's like one from there's one from Mac Engine. There's one from Stewie Hershoe. There's one from, I think Megan has one. There's a handful more. What do you think about this experiment? I think it's interesting. It's obviously, limited, as in it's not going to be foolproof. I haven't used it. I've seen what it does. I know what it does, and it is better than nothing. But it's not going to be, it's not the complete solution. I think that the core team people, what? Once my Lugg comes online, we can ask him. But the core team knows that this stuff can be done. Hey, Lugg. So you're alive? Wait, are you screen share with me? Okay. So where's your screen share? Do you also want to do the screen share or not? You know what? Wait, let's do this. Okay. You mute the stream. I mute myself from the stream. Everybody give me a moment. And Yeah, I'll set everything up with Lugg, and then I'll be right back. We are gonna need just a minute or two to get everything up and running. So I'll be right back. Okay, everybody. We did the setup. Let me put Matt on screen. There we go. Here it is. Here's his webcam. I think they can also hear you.
I can. Hopefully, I'm audible.
Yeah. Does everybody confirm that? I think it's not needed. It works. Okay, so let me see. Let me set up also screen share. There we go. We also have screen share from you.
Nice.
Maybe we can make it smaller or something to. Yeah. Yeah. Okay. How's the quality of the screen share for you?
For me?
Yeah, for you.
Yeah, it's perfectly fine. I can read everything on screen. I can read scene and all that. Oh, sorry, I can read bulk and all that. Yeah.
Okay, perfect. So I think we're good to go. I haven't announced that the stream yet on social media stuff, so I guess let's go do that. I'm like face reveal. Wait, I think he streamed. Did you not stream with your webcam on?
I don't remember if I had a cam or not. I've never been secretive about my face. But I've definitely streamed with a webcam in the past. I don't know if I've streamed when I streamed compiler-dev stuff, that was with a webcam.
Mm-hmm. Okay. Now everybody can take a good look. Okay, let's post on social media.
Don't mind me reaching around the corner. I just thought I should check if I have something that might be handy.
Okay, nice.
Totally don't matter. It's fine.
So next thing for me is to make warm up some tea in the microwave with the bag dipped into the cold water, as one does. And I think then we can start. Can you show us some anime stickers? I don't really have anime stickers. I have Zig stickers, but I have a ghosty sticker. Look, I'll show you my ghosty sticker.
It's a good sticker.
Yeah. You know, when there were discussions about whether to make ghosty stickers shiny or opaque, I was going for the opaque one. I was saying, no, do the opaque one. It's going to be so much better. And then I decided that I liked the shiny one more when it came in the mail.
One sec. Potential technical difficulties. My second monitor just turned off for seemingly no reason.
Okay, so here's what I would say. You figure that out. I go make my tea. Let's put a countdown. So let's say that we start with the main content in, let's say 10 minutes from now.
Sure, yeah. Okay.
He's not crashed. He just turned off the webcam temporarily. Okay, be right back. Okay, I am back. Unban. You better unban me. Okay, so we did everything, right? We announced everything. Oh, there's a Telegram group that I'm gonna announce to. Okay, should I put like some kind of sepia filter to the stream to give it a even more noir vibe? Actually, maybe I just have it in OBS already. Where do I put it to the full scene? I could put it to. Okay, let's try. Give a filter to the full scene. There's like color correction. Yeah, but that doesn't immediately tell me how to do sepia. So like I can mess around with sliders, but that doesn't really immediately answer the question. So no, this ain't it. Vintage filter OBS forums. Oh man, I should have done this earlier because I can't load a plugin at runtime. They should have put like a screenshot though. Like, how does this thing look like, man? Oh well. Oh well. Never mind. Okay, let's see how's Lugg doing. Is he alive? Isn't? Oh,
I am alive. I'm here.
Hello. Okay, did you figure it out?
Oh yeah, the monitor fix was 5 seconds. I then went to make tea.
Oh, I see. Oh, so you were also doing the same.
The monitor fix, as far as I'm aware, was just a power cable being loose.
Okay. Let's see. So we have, I think, one last thing to worry about, which is. So here's my idea. Here's what I'll do. I will keep this on all the time. I have a question for you. Can you disable your screen share in the same way that you disable right now your camera, meaning not interrupting the stream, just like toggling it off temporarily?
I mean, all I did was click the button here, so I can try doing the same thing.
That nuked it though. So you will okay, re-screen share.
In theory, I am. I don't know if it's worked though. Oh no, it's not. Okay, I want.
No, you'll have to do the full procedure again. Yeah.
Okay, now it's back on.
Like, yeah, you didn't like pause it, basically. So there is no way of pausing it.
Not as far as I'm aware.
Okay. So then I guess I will manage your screen share, meaning I will turn it on and off based on our needs, I guess.
Yeah, that's fine. I don't think we'll need to toggle it too much.
Okay. So how do you want to do this?
Well, I have. I don't know what they were at this point, but I found 2 bugs, which would be lovely intro to compiler development. So I can just sort of give an outline of what we're going to be. Oh, stupid! Sorry, it's opened my launcher on the wrong screen. That cool.
Okay, so what I would say is maybe send me the link so I can take a look. I mean, okay, you are screen sharing also the browser, okay?
Yeah. So these are 2 issues from Jacob.
I see.
Very similar in scope.
It's a bit small though. You know what? I think it's better if I do it on my screen.
Yeah,
so
okay.
yes, if you can send me a link.
Yeah. Let me. I can't type. I've sent you on Discord 2 links.
Okay, SEMA incorrectly multiplies float vectors containing zeros at count time. And then copy link. Incorrectly simplifies runtime float vectors multiplied by zeros. Okay, so which one you want to do first? And probably you should take some time to understand what the problem is, because that's not obvious to me.
Honestly, I don't mind which we do. So the way I was thinking we do this is that I can, firstly, Loris can reach across his room to turn on a light.
Yeah.
Is that I can do one of them and kind of walk you through the process.
Okay.
And then you can try and use that to figure out the second bug.
Okay. That sounds good to me. So then pick one and let's try to understand what the problem is with that one.
Sure. Well, shall I do the one you have on your screen right now, 22743?
Okay.
So I guess what I should really do first is kind of explain kind of the Zig compiler pipeline. I mean, obviously, Loris, you'll know some of this, but you have a whole audience of people who might not.
Yeah.
Let's see if I can draw things on here. I mean, yeah, whatever. Can you throw my screen share? Ah, yeah, brilliant. Let me. No, that. Okay, so as with most compilers, the Zig compiler kind of works in stages. So you kind of have at the very top you have the source files, your like .zig files. At the very bottom you have your binary, and there's just a bunch of kind of discrete steps in the middle.
Yeah.
That's sorry, just to void chaos father. That's not Arch. It's void Linux. So yeah, at the top you have source files. I'm trying to write on a trackpad, and I am not good at it. I'm going to not even try and do that. So you have source files at the top. That's .zig. Zig.
Nice.
And so the first thing we want to do is we want to turn this into an AST. AST is an abstract syntax tree. Anyone who's done any kind of compiler development before will know what that is. But essentially what we're doing is, there's actually kind of 2 steps here. I've kind of skipped a step. But the trick is I don't care about this stuff. Essentially what we're doing is we're taking, so you might have like an if statement, right? So you might have if, and then a condition in parentheses, and then like one block of code, else another block of code. That as just a stream of text isn't very helpful to the compiler. What it really wants to know is sort of, it wants to turn this into a tree structure. So you want to say, if this, then this, else this. So it wants to add a lot of structure, which is only kind of implicitly there. It's like we understand that it's there, but it's much harder for the compiler to understand that. So what it's going to do is it's going to make this thing called an AST, which just adds all of that structure. So you get this big tree starting from, for each file, you have like one node at the top, and then kind of each declaration in the top of the file, for example, is a node beneath that. If you have an if statement, then it'll have 2 or 3 things beneath it. A function will have like the parameters beneath it, and it will have the body beneath it, and all that kind of thing. So that's called the AST. That was a terrible box. That's the AST, the abstract syntax tree. Getting from source to that is called parsing. I really should. The thing I was trying to find out my bag earlier was I have an old graphics tablet, and it's really bad, but it would have made this more tolerable. There
you know,
go.
there's also the online graph tools that people use sometimes.
Yeah, I should look into that kind of stuff.
Yeah. In any case, this is plenty good.
Yeah. So we have an AST. That's good, but there are a few more stages. So the next thing the Zig compiler does, we're now delving into sort of details of the Zig compiler rather than things compilers in general would do. But next, we are going to make a thing called ZIR. There. This is stands for Zig Intermediate Representation. And Loris will know what this is. But
I'm deeply familiar with it.
Yeah. Because the old version of Autodoc, which is the documentation generation tool for Zig, used to operate on ZIR, which was flawed in many ways. But it means that, yeah, Loris kind of knows what's going on here. But essentially, ZIR is we're taking the AST that we've generated and we're turning it into sequences of instructions. So it's kind of, they're not particularly low-level instructions. So when I say instructions, you might think of like assembly or something like that. It's nothing like it, or well, it's not really like that because, the instructions are a lot more high-level. They involve things like type checking, and also instructions can kind of nest. So I can show you. I will show you what this means later because we can actually look at some ZIR. This is a really easy thing to look at. But we'll quickly finish running through the pipeline first. So the process that creates ZIR is called ASTgen, ASTgen, whatever you want to call it. ASTgen. Cool.
So Jericho is asking, how does it compare to LVMAR? Same level of abstraction, any big differences? I think I'll try to answer this and then you tell me how correct you feel my answer is. I think it's very different because ZIR is not concerning itself with the same type of things that LVMAR is concerning, I think, at that point. So as Matt was saying, with ZIR, it's basically, you're not yet trying to get to implement all the logic and like lower it to instructions. You're basically still orchestrating something that is in between semantic analysis and parsing. It's like parsing plus, maybe, or SEMA minus. Well, because ZIR is the input of semantic analysis.
Yeah. So kind of, I'd say the most important difference is that at the point of LLVMIR, you've lost a lot of type information because you don't need that to do optimizations. In fact, it's often actively harmful optimizations. So you've thrown away a lot of information at LLVMIR and you've generated quite a simple IR. ZIR looks a lot more like the original Zig code. It doesn't look like it, but kind of structurally, you can see the Zig code there and it contains all the type information. Comp time logic hasn't been evaluated yet. So that's all going to happen in the next stage. Also, Andrew in chat saying you'd expect ASTgen to generate AST and ZIRgen to generate ZIR. Yes, that's probably fair. This name, I don't know where this name came from. I'm not sure. I'm pretty sure the Bootstrap compiler also had a thing called ASTgen. So it might just be a very old name from Andrew Kelly that we are stuck with now. I mean, we could change it, but like it doesn't matter that much. But yeah, you have ZIR, and there is there's kind of one bit of ZIR for each source file. Okay, so that's the easy bit. How do I scroll down in here without Alt Shift? Okay, this is fine. Scroll bar, sure. Okay, so ZIR. Now is the fun bit. So the next thing we're going to generate is called AIR. AIR. No prizes for guessing what these two letters are, intermediate representation again. But the A here, so what's going on here is that kind of almost the defining difference between ZIR and AIR is that ZIR is before we do type checking and comp time logic and comp time control flow and all of that kind of thing, essentially before we do semantic analysis. AIR is after semantic analysis. So the code has been analyzed, hence analyzed intermediate representation. So any comp time loops, for instance, have been unrolled here, and type checking is done. We know that so essentially, once we reach AIR, we pretty much know that code is valid. There are a couple of asterisks to that, but we're not going to worry about those asterisks today. And so the process of getting from here to here is with a thing called SEMA. SEMA. Oh, that writing was going so well until that A. Good enough. So it's called that because it's doing semantic analysis. This here is the bit we're going to mainly be looking at today, because it's I would say one of the most interesting parts of the compiler. I definitely think the most fundamental part of the compiler. It's kind of the thing that makes Zig Zig, in a good sense. There is a bit more past here as well, of course. So because, computers don't know how to run AIR, so we, from here, want to end up at a binary. And there's actually a couple of stages here, but we're not going to talk about them right now because I've run out of space on this document. So essentially, there is more stuff here. Specifically, we're going to run the code generator, and then we're going to run the linker, but we're not going to worry about those today. We're going to be looking at SEMA. You should lower the volume of. Right.
Sure, I can.
This gives me a second to drink some delicious tea.
Okay.
Okay. So yes, in chat, all comp time. Yeah. So all comp time logic happens between here and here. SEMA is responsible for all comp time. So we know actually, even just looking at the description of the bug that we're going to be fixing here,
Okay.
I mean, ignoring the fact that it says SEMA in the title, because Jacob knows how the compiler works, we can see here that this is happening. What's happening with this bug is multiplication at comp time isn't quite working. Right. Sorry, let me zoom in a bit there. So multiplying vectors of floats at comp time doesn't quite work how it should. Because it's a thing happening at comp time, we know that SEMA is doing it. So we know where we need to look in the compiler. Okay. So let's take a look at this bug, shall we? Don't need that document. So I am in my Zig repo. The directory is called master just because I use Zig Git work trees, so I have a horrifying number of folders.
Wait a second. I fear you might be jumping ahead a little bit too fast. What is the problem? Can we look at the example and see what the problem is wrong? Like there's something wrong and understand it from the provided example?
Yeah. Well, what I was going to do first was just show like building the compiler, and then we can kind of reproduce it with the compiler we've just built. Is where I was going to go.
Understood. Makes sense.
So, I need to teach myself not to. I have a bunch of aliases set up in my shell, which let me just write that to build Zig in ways that I commonly do. We're not going to do that. I'm actually just going to run this command quickly to update my system Zig install because I think it's a bit outdated. Give that a moment.
Wait, that's not Marlo's Zig up.
No, it is a script I have named Zig Up, which was named before I realized that the project Zig Up existed.
I see. It
is like a 3-line shell script. Okay, so what I'm going to do is I'm going to write Zig build. I'm going to say no lib. So this option, when you're building the compiler, basically says, by default, it's going to copy all of the library files to the prefix. So that includes the Zig standard library and all of the libcs we distribute and all of that stuff. Copying that stuff takes a while, and if we're not actually generating a binary that we want to distribute to the world, we don't need it. So
yeah,
generally, when you're doing compile development, you'll just pass this option when you're building.
It also lets you just change the standard library. Like if you're developing the standard library, you just change. So sorry, maybe in case it's not clear, but he's not copying the standard library, but he's doing this inside of the Zig repository, which has a copy of the standard library. So Zig has this logic that a startup searches for the standard library directory from the directory where the executable is going upwards. So basically, by not copying the standard library into the output directory, Zig will pick up the copy of the standard library that is in the repository. So that would be like, the Zig repository, ziglang/zig/lib. And so that way, by modifying the files that then you want to commit in the repository, those changes will be picked up by Zig right away. That's also convenient.
Yeah, exactly that. So yeah, if you didn't do this, then you'd have to instead edit the standard library that was in your prefix folder. And then if you rebuilt the compiler, it would be overwritten, which is all just very awkward. So much easier. Just pass this option and work off of the lib directory here. Okay. So we have that option. And also we'll see how fast this goes just for fun. I'm just going to move this less to my screen. Okay. The other option I'm going to pass is use LLVM equals false. So this is going to tell Zig, by default, it will build things using the LLVM backend. With the LLVM backend is it's really slow because the LLVM backend isn't really slow, but LLVM itself is really, really slow. So if I didn't pass that, we'd be waiting a minute or two for the compiler to build, and I've not got time for that. So instead, we're going to pass this, which says to use Zig's own code generation backend, because I'm on a x86-64 system, and our backend for that works fairly well at this point on Linux, not so much on macOS or Windows. So if you're on that platform, you can use this, and you'll get much faster builds. So anything else need to pass? No, that should be it. So, okay, first it's going to compile the build script, which will use LLVM. In fact, what I'll do is after the build script compiles, I'll Control-C and rerun this so we can see how long the actual compiler build took. Give this a moment. Okay, so I'm going to cancel that.
I think if you did summary all, you would get that behavior anyway.
Good point. Let's do summary all. Okay, that's a really good start. Oh yes, a important option that I missed. Sorry, we by default, because what I'm using here is my system installation of Zig, which is fine because there aren't any issues with that right now. Sometimes there can be conflicts, but that's generally fine. However, there has been a change to the standard library recently, and the Zig compiler wants that new version of the standard library. But by default, this is going to use the version of the standard library that's installed on my system. Which is different, doesn't have the things it wants. So what I need to do is pass this option. I'm just going to full screen this. Zig lib dir lib. So this tells the compiler, I know that you really want to find lib like in my system installation, but actually don't do that. I'm telling you where the path to the standard library and all of that stuff is instead. And I'm telling you it's in the folder right here named lib. So this is the folder Loris was talking about earlier, which it's in the repository root, and it contains standard library and all of that stuff.
Yeah.
So now...
Jericho, you got an answer already from Andrew, but just to reiterate it more clearly, if you see the -d use LLVM is a custom flag that has been specified in the build.zig file, right? So it basically, to even parse it and understand what it does, first you need to run the build script. And to run the build script, you have to compile the build script. So the first compilation does use LLVM to compile the build script, but then after that, it will not use LLVM anymore. And in fact, now that's compiling the compiler, you will not see LLVM emit. You just see alf flash.
Okay, there we go. So yeah, actually building Zig there took about 20 seconds. We're trying to get that down. It's still not great, but it's a lot nicer than the minute or 2 minute dev loop that you have with LLVM. So what I have now is zig out /bin/zig, and this is a zig compiler. If I run it here, I get a help menu. So, okay, we can zig. Step 1 done. The next step is try and understand what's going on here then. So what I'm going to do is just make a file repro.zig, and I'm just going to paste the repro from the issue into it. And because Jacob is good at writing issues, it's actually a full reproduction, and I don't need to add any code. So before we run it, let's actually just take a look at what's going on here. So importing the standard library, and we're getting nan. So this is the function which you give it in a float type, and it will return you the nan value, nan being not a number, which is a weird float value that has all kinds of weird properties. And then we're at comp time. We're going to take a nan, an F32 nan, and we're going to multiply it by 0, again as an F32, and we will print the result.
Right. And that's supposed to give nan, I believe.
Yes, correct. So nan is a weird value which is kind of viral in a lot of ways. So generally the case that doing an operation on nan will return nan as the result.
Yeah, by the way, if you think about it, that's freaking insane. It's like multiplication of floats has like, there's a name for it, right? In algebraic terms, like the, oh man, like the sponge value, like the absorbing value, the one that you apply that operation with that value and always returns that value. For multiplication is 0. Any number multiplied by 0 is 0. Well, normally.
Okay. I don't remember the name of that, but yeah.
Yeah, so it's funny because I think normally you don't have more than one, I think. I don't remember all the exact rules for algebraic theory, but yeah, it's funny that nan is like basically breaking a bunch of symmetries in how floats work.
Yeah. Someone asked how is nan represented in memory? Well, funny story, there are actually loads and loads of nans. It's a property of the... we probably shouldn't get too much into the float representation, but we can take a quick look. I think there are some good online things. Let's see what this does. Let me zoom in a bit. So this is a online tool that, as far as I can tell, will convert between like a 32-bit float, which we can customize each bit by ticking these boxes, and will tell you what number it actually represents. So, like, for instance, I can make -0 by turning on this bit. -0 is not the same thing as 0 in floats because floats are incredibly strange. I can tick some things here and start getting some values. I can knock the exponent up. So floating point is it's kind of like scientific notation in like when you're doing like maths in science. You won't typically write, 5 billion. You'll write 5 times 10 to the 9. And floating point is doing the exact same thing, but in binary. So here, for instance, I've made a nan. So this is just a bit pattern which these this specification, IEEE 754, says this doesn't mean any specific number. It's just one of many nans. So I'm guessing I can probably do pretty much anything to this mantissa and it's still nan.
Yeah, except empty, because it's infinite.
Except what, sorry?
Yeah, except empty. Empty mantissa is infinite. Any value past infinite, in a sense, is nan.
Yeah. And yeah, I can also set the sign bit, and that's a different kind of nan.
Nice.
And there's, I don't know where the distinction lies, but there are things called signaling nans and quiet nans. But I don't actually know what the difference is between the bit patterns there. Maybe it's the sign bit. I don't know.
Me neither.
But yeah, there are all kinds of nans. The bit representation of floating point numbers is really weird, and we just have to go with it because CPUs are really good at doing it now. So yeah, we're stuck with this.
I mean, this kind of explains why historically, like hardware had a separate device, right, for floating point. Like you have the FPU that was, it clearly needs to be very different from anything else from ALUs because, like, this thing makes no sense. It's like it's a bunch of conventions.
Yeah, like to this day, x86, 64 machines have, as you say, the FPU, which is often called the x87 FPU. It was originally an extension to some old x86 CPUs, but it's a really slow, really bad, you shouldn't use it way of doing certain floating point operations. The really fun thing about the FPU is that it supports 80-bit floats, which are a really weird kind of float, which basically no one else supports. But because the FPU supports them, everyone, like every programming language that wants full compatibility with like C APIs needs to be able to support F80. It's a very silly state of affairs. But okay. Yes, right. So back to the repro. We're taking a nan, multiplying it by 0, and we expect the answer here will be nan. And if we actually peek down here at the output, we can see that it is nan. So that one's working fine. Then what are we doing? Okay, we're making a vector of 1 F32, and we're putting nan inside of it. Okay, that makes sense. And we're taking a vector of 1 F32, putting 0 inside of it. So, Loris, what do we think the answer should be here?
Right, it should be a vector with a nan inside, but it seems that that was not the case. The 0, 1, apparently, this time.
Yeah. So, because vectors do arithmetic element-wise, we expect this to be exactly the same as just putting the result of this inside a vector. So we expect a vector that contains nan, but instead we get a vector that contains 0. That's wrong. Okay, let's check if we can reproduce this first. It's going to be really embarrassing if this bug's been fixed without me realizing in the past few days. Not that. Zig out, bin zig, run repro.zig. So this AST lowering thing here is actually the compiler running ashgen, which we mentioned earlier. You normally don't see it because it's really fast, but because we're using a debug compiler here, and in particular a debug compiler built using the self-hosted backend, which is quite slow, which generates quite slow code, I should say, we very much do see it happening. This is actually running slower than... Okay, there we go. Okay, good start. Because I did run, we're getting this. That's my bad. Let's instead do build obj. This is actually a top tip of testing compiler things. Build obj is generally a really fast command because it doesn't need to bring in all of the like standard .start machinery, which like building an executable generally does. So usually if you're making like a minimal reproduction of a bug, particularly if you want to look at like the outputted binary or something like that, you're going to want to use build obj because it's as minimal as possible. So if we do that now, okay, much faster, and we can see, yeah, we got the same thing that Jacob did. Nan here, which is correct, 0 here, which is wrong. Okay.
Andrew is saying that 1 to the nan is 1. No, I don't believe you. I mean, it could be. Did they actually define it that way? That is insane. I mean, I guess there probably are reasons to do this kind of stuff. But holy cow.
Yeah. So now it's time for some to try and understand this bug.
Yeah, because 1 to the anything is 1. Well, also anything multiplied by 0 is 0, except nan.
Yeah.
Okay, sorry. Let's go back to the main thing.
Okay. I'm kind of interested in the nan talk now because once the nan JS
yeah, we're now deep in nan philosophy. And by the way, these fucking Ziggy people, so it's not enough undefined behavior. They now want undefined numbers, and like they enjoy discussing undefined numbers, right? Why would you even have nan in your language?
That's a good question. Okay, so what are we going to do? Yes, we're going to use our compiler. And earlier we were talking about kind of the list of stages, like the compiler pipeline. Kind of wish I hadn't closed that document now. But we kind of want to know, where should we be looking in the pipeline?
Right.
Well, we know that because something's going wrong at comp time, we're probably going to want to look at SEMA.
Yeah.
But what I'm interested in first is what's SEMA actually being given? What's the ZIR that's going into it? This is helpful to know because then we can see what instruction is doing this multiplication, and then we can try and look at how that instruction's working and delve into the bug.
Right, how it's handled in SEMA. Oh
Exactly.
man. Now, now I get it. Basically, SEMA is doing the same thing that I was doing with Autodoc, just more seriously. So it will have somewhere a switch with all the ZR instructions, just like I used to.
Yeah, totally. We will look at that switch in a minute if you want.
Yeah.
But okay, so what we're going to do here is people who use Zig may be familiar with the check command. It just spits out, so it does some basic checks over the file and will spit out diagnostics if there's anything wrong that it can see. For instance, if I put like a unused variable here and I run check, then it will tell me unused local constant. Oh no, I've just started to flame war in the chat about whether unused variable warnings are good or unused variable errors are good. But the way it's actually doing that is it's just running ashgen over it. So it's running the parser and then it's running astgen. So this process actually outputs ZIR. We just don't see it because obviously the compiler normally doesn't want to show that to you. But because we've built a debug compiler here, there is a special option which ashcheck now supports, -T. I don't know why it's T. I have always wondered this.
Text, maybe? I have no idea.
Maybe. That seems likely. But if we run it, ooh, we get some stuff. Let me full screen this again. What we're seeing here is a textual dump of the ZIR that's been emitted. So kind of the way this looks is, let's just take a look at, for instance, this line here, for sake of example. So at the start, we have %15. The percent means nothing. It's just sort of a residual we have. But this is saying that this is instruction number 15. They won't necessarily be printed in order. The numbers can jump around a bit. This is just so that we have a unique identifier for every instruction. And then this instruction is vector type. So this is going to be an instruction which corresponds to the @vector built in. So it's creating a type. So this is actually a good demonstration of how ZIR is different from LLVMIR, a question we had earlier. Because in LLVM, like, you already have types. You don't need to use instructions to create types. But because ZIR is happening before we've done any comp time evaluation or any type checking, yeah, it contains instructions to create types and things like that.
So it's is it correct to say that, for example, instruction 16 is literally there to make sure that SEMA sees that instruction and validates that the initialization of that vector, the value matches the expected type?
Yeah, exactly right.
Okay.
Well, not quite what we said, but essentially this instruction is validating that we are allowed to initialize this vector type with a array initializer.
Oh, it's not checking the
array
value.
initializer of length 1. So that's what this
I see.
1
But
is
somewhere there is a type checking for the value that maybe I haven't seen.
Yeah, that'll be happening in the array init instruction down here.
Okay, so it's implied in there. Okay, so so here's a question then. Why do you have 16 as a separate instruction? Why does not, for example, vector type imply that you need to do that validation?
Because the problem is, essentially, this is because of result types. So the way Zig evaluates expressions like these is that the expression in here might have been something like, instead of nan, maybe we wrote something like float from int 1, 2, 3. And built-ins like this need to know what type they're expecting, because otherwise, I mean, how are they going to, like, you can't make a float without knowing what float to make. And so in order for this to work, we need to know the F32 as a type we can forward. But in order to know the type to forward, we need to have checked that this expression even makes sense, right? Because if it doesn't, if I just wrote like
like 7 instead,
then I mean, there's no type we can put forward there. That initializer doesn't make sense. So simple operations like this can sometimes be exploded into quite a few instructions just to make sure everything happens in the right order.
I see.
So if I run this again, let me actually put it into less. That might be a bit easier. Then where were we? Yeah, so after the validation, you can actually see we have an instruction called array init elem type. So this is actually saying, tell me what the type is that I should forward.
This
so
0
because,
to,
yeah, so specifically forward to element 0 because it might be different for each element because of tuples. So this is going to say, okay, well, I'm going to look at instruction 15. Oh, that's a vector type. And I'm looking for element 0. Well, element 0 of this vector of F32 is an F32. So that means the kind of result of instruction 17 is the type F32. Making sense?
Yeah.
Cool. So what we were wondering is what's doing this multiplication. So we can take a little look through this code again. Well, I mean, I can see an instruction that really looks like it's doing a multiplication. It's called mul. But if we weren't quite sure about that, what we could do is sort of read through this bit by bit. So we know that, buttons, there we go. We know that this is kind of the indentation level we're interested in because we can see that this is the inside of a declaration, specifically a comp time declaration. That's what this is telling us here. And so within this declaration, okay, what's going on? So decl val, this is saying, this is to do with referencing another like global declaration. So you'll see that if we look in the code, the first thing we do here in this block, like obviously, I mean, the first bit of code is this, but before we do the compile log, we need to evaluate the arguments. And before we can evaluate the multiplication, we need to evaluate the left-hand side. And before we can evaluate this function call, we need to know what function we're calling. So you're kind of going, drilling like as far down the tree as you can to kind of see the first thing we're doing. And the first thing we're doing, it turns out, is getting this function nan, which is a different global variable. So that's going to be what that decl val we saw is doing. This is saying, get me, like, return the value of the global declaration nan. When I say return here, I just mean have this instruction return. So that means later we can write %7 and we mean that value nan, that function. Okay. After that, we have the a debug statement instruction. You can pretty much ignore these when you're reading ZIR. They're occasionally helpful for telling you where in the code you currently are, although actually these numbers also do that. In fact, I forgot to mention, yeah, this bit at the end you can also pretty much ignore. It's a source location. So the token offset is just telling us details about how the source location is stored. And then this is the line and column span. So this tells us that this reference to nan is happening on line 3 from columns 17 to 20. And so debug statement here is actually giving a very similar piece of information. It's just that this one's for debug info rather than for like compile errors. Okay, so yeah, we can pretty much disregard this instruction. Not interesting to us. But then we can see, oh, okay, we're calling this function. And then inside here is the list of arguments. And the argument we're going to pass here is the type F32. So when you see an @ sign like this, that's kind of where we have a special name for a value, often as a kind of optimization. So for instance, a couple lines below, you can see @0. Obviously, we don't have like one of these for every possible numeric literal you could type in. If you type 187, we don't have @187. That would be very silly. But 0 is a really common number to type, and so is 1. And there are a couple of other, I think -1 might have a special thing as well. So rather than dedicate an instruction just to getting that number value, we say, okay, we have a special way of referencing that. And AshGen figures all of that out for us to kind of emit more concise ZIR. So in this case, this is a special value which just refers to the type F32, representing the fact that the first parameter to nan is F32 in the source. Making sense?
Yep.
Cool. Okay, so this is the left-hand side of the first multiplication. Now we're going to need the right-hand side. So what we're going to do here, because the right-hand side is just as, like if we go back and look at the code, it's just this as f32.0. So that's exactly what it says. As underscore node, ignore the node bit. That's just a weird thing with the naming of this instruction, because there used to be a few variants of as which store the source location in different ways. But this is pretty much the only one you'll see anymore. But we're saying as the f32 type, the value 0. So this is just, this instruction just represents the corresponding, like the right-hand side here. Cool. You've got the left-hand side, we've got the right-hand side. Next, we need to multiply them. So that's going to happen through this mul instruction. And here, we're not actually using any like constant values with an at sign anymore, where both of the operands here are referring back to earlier instructions. So multiply the result of instruction 9 here. So that's our function call to nan, with the result of instruction 11 here, which is the like at as we just did.
Yeah.
Okay. So at this point, we know that like when you have a multiply sign, like a star sign, it turns into this mul instruction. So we can guess that's probably where the bug is. But we can continue going through some of this ZIR quickly.
Yeah, but this one, in any case, is the runtime one. So this is the good one, right? So
not the runtime one, but like not in a vector, as in.
Oh yeah, you're right. Not in a vector, right?
Yeah,
not in a vector. So this one is okay.
However, we can predict that the ZIR is going to look the same for the other one, because what's important to remember is that AshGen, which is generating the ZIR, knows nothing about types. It doesn't know that the first one's a scalar and the second one's a vector. It has no concept of that. It just knows I saw the multiplication operator, so I need to tell SEMA to do a multiplication. So it's pretty much always going to emit the same ZIR, regardless of things like types. But we can quickly look through a few more things here anyway. We have extended compile log. So extended is just to do with how we actually store ZIR instructions, which we'll get into a little bit later. This is basically just saying this is a less common instruction, so we're using a slightly less efficient way of storing it. So when reading ZIR, you can pretty much ignore the word extended and look at what parentheses instead.
There's basically one level of indirection, right? It's a way of saving bits in, let's say, in an enum. And so uncommon stuff is squished under extended. And then when you know that you see extended, then the value will tell you that then instead of seeing immediately like the first argument you put in, the next value instead will going to be what specific case you're in. And you have to look for that elsewhere.
Yeah, exactly right. So in this case, we have an extended compile log instruction. So, I mean, no pros for guessing. That's for the compile log built in. And we're just saying log the result of instruction 12. That's our multiplication. So this makes sense. Ensure result used is just an instruction which basically says, like, this is, we've just evaluated a statement. And in order to make sure the user isn't, like, accidentally ignoring something, we need to make sure that that statement is void. Because otherwise it would mean you could just write like 1 semicolon in a function and it would happily evaluate the value 1 and throw it away silently without you realizing. But because you'll get this instruction in that case, this is going to tell you, well, hold on, you have a value here and it's not of type void, and you're just like not even explicitly ignoring it. You're just not using it. You need to change that. If you write underscore equals, then this instruction is replaced with a different one, which just checks that it's not an error, because you're not allowed to do underscore equals with an error. But yeah, that's what this instruction's doing. Make sense?
Yeah.
Cool. So we won't bother going through all of the rest of this, but suffice it to say, it's pretty similar to the other stuff, but we also have some stuff with vector initialization here. So this is corresponding to the call to @vector, and then this is just some machinery to say make sure we're actually allowed to initialize that. Then we get the child type of the vector. We get nan again because we're going to call it again, and yeah, we call it again. Then we do an array initialization using that value. So it's a bit more complicated, but what we're interested in is that down here we're using mul again.
Yeah.
So we know for sure that this is going to be where we're expecting to see the problem.
So what we expect to see then is that in SEMA, there's going to be a branch where we deal with mul. Somewhere in there, there's going to be some call that tries to somehow evaluate for some definition of evaluate what instructions 22 and 26 resulted to, and so, well, in the case of 9 and 11, so the first mul, the code that deals with them is okay, but the code that deals instead with evaluating to a vector does the wrong thing instead.
Yeah, exactly. Okay, so from here, what we could do is, in fact, what we can do here is we can take a look in SEMA, which is a big scary file, but don't worry, I'll keep you safe. And we can kind of take a look at where this instruction is going to be evaluated. And before we actually solve the bug, we can also take a step out and see if we can look in a debugger and see what's going on.
Oh, nice.
Yeah. So I'm going to open SEMA now. SEMA is a big file. SEMA is 40,000 lines. Not the biggest file in the compiler anymore, but used to be. So earlier, you were actually talking about autodoc, and you said, like, oh, SEMA's going to be doing the same thing, where it has, like, a big switch over all the instructions. Let's find that switch. It's called analyze body inner. Big dot comment with things that you don't need to understand right now because it's weird details of how things like comp time control flow work. But you can see here, yeah, big old switch, every instruction. And most of these instructions are actually just calling a handler function. That's how we've generally structured this. And if I scroll down a bit, you'll see, oh, these are ones which look a bit different for optimization reasons. This is a special instruction which we'll never see here because reasons. And then these are the extended instructions we were talking about. So these are ones that are much less common. So we've decided to put them in a separate enum, which means that our main instruction tag can be 8 bits, 1 byte, which saves a lot of memory. So then, yeah, there's all of these less common ones. Some of these are actually handled inline here, again, for reasons to do with just optimizing this very tight, very important loop. There's actually quite a few of those if we continue scrolling, and we continue scrolling, and this is a really big one. This is to do with comp time control flow. And at the end, so the result of this big switch is this thing called a air inst ref. So a ref essentially means a value. So specifically, this is telling us that it's either going to be a comp time known value or it's going to be the result of some AIR instruction. So remember that AIR is the thing that SEMA is actually generating. So any runtime code is going to correspond to AIR. But if you're doing comp time logic, there isn't any AIR there. Are you having trouble with BOR?
Yeah. You know what? I think I'm confident that YouTube is what breaks emotes.
Wow, really? Sorry, I've not been keeping up with your stream for a few days now.
Yeah, I think that's... I need to debug it. I've been lazy, but it happens after like 1 hour that it's been running. And I, you know what? Let me double check. I bet you they were live for about 1 hour. Yeah, we've been live for about 1 hour. And oh, God damn it. In any case, yeah, we're good. Hello, Porky Shimwell. Sorry, everybody. Send again your messages with emotes. Now you can.
My screen just turned off again, but now it's turning back on. So, okay, we're back.
I think it might be YouTube in Borg that kills your screen at this point.
What, it was protesting earlier towards the start of the stream. And now it has like an hourly protest where it'll...
Okay, so we're looking for mul, right?
Yeah. So firstly, I should just finish explaining this.
Oh yeah, what's ref? Can you go to definition on it?
Yeah. Well, I don't have ZLS installed, but I can tell you where this is defined. So let's just close SEMA for a second. Either a reference to a value stored in the intern pool, which I will talk about in a second, or a reference to an AIR instruction. The most significant bit is a tag bit, which basically tells us which of those two things it is. None is weird, but don't worry about that. And there are actually, so the intern is how we represent values in the compiler, like comp time known values.
Okay, I get it. So it's an index basically inside AR, but with a prefix for common stuff.
No, it's an index into either AIR or the intern pool.
Oh, okay. Sorry, yeah, in one of the other, yeah, but some values are special, some values are reserved.
Yeah, we have a bunch of special ones which correspond to special things in the intern pool, which are special, very common comp time known values.
Yeah.
So what we can actually do before we head on to mul is we can look at a really simple instruction. I think the simplest instruction here is probably in comp time. So the built-in, like at in comp time, just returns true or false depending on whether it's evaluated at comp time. Really simple. So if I search for in comp time in this loop, oh, I can find it. It's calling this function zir in comp time. As a general rule, most instructions are handled by a function called zir followed by the instruction name. That's not always true. For instance, here you can see 3 instructions which will actually call the same function. But generally, that's going to be the pattern. So if we look at zir in comp time, this is a really simple one. So this function takes 2 arguments. It takes in SEMA, which just contains all of the states like about this semantic analysis, and it takes a block. Block is kind of a context. It tells us about the current, well, essentially the current block of code we're analyzing. And the bit of state that it contains that we'll be interested in here is whether we are evaluating at comp time. Using this function here is comp time. And so all we're going to do is we're going to check this, and we're either going to return true or false. The things we're returning here are actually some of those special values that you picked up on in the enum there.
Yeah.
So like true and false have special values. Certain common types do, such as like U8. Like the value 0 as a comp time int has it. So it's actually, there's a lot of overlap between those special values and the ones we saw in the ZIR earlier.
Yeah.
In fact, when I say there's a lot of overlap, they are exactly the same. It's an optimization with how these parts of the pipeline interact.
So how does is comp time work? I'm guessing it's saying yes if it's a comp time block, and it's saying yes.
Yeah, it's really simple. So the only reason it's actually a function is because we don't have like a Boolean field. We instead have a field that says why a block is comp time.
Right. So it could be comp time keyword, global scope, nested declaration, type declaration in a function body. I'm guessing.
What were you just listing reasons?
I'm assuming those are like, is it expressed that way?
Yeah, so it's like there's kind of a couple layers of nesting.
Matt, if you had ZLS, you would just go GD. Every single time you just do GD and you jump directly to the destination. Just saying, huh? By the way.
I know. I used to use ZLS. I didn't like it very much. Also, frankly, you wouldn't do that in SEMA because SEMA makes ZLS explode.
Okay.
ZLS, last I checked, cannot cope with really big files at all. So yeah, there's kind of a few layers of indirection for silly reasons, but kind of most of the reasons are this thing.
Okay, so
simple reason, which is an enum here.
Oh, there we go.
Yeah, there's all kinds of things. Which I kind of
right, because like also if you're like an argument to a comp time to a built-in that only gets evaluated, that's another case. Okay, so
it's things like this.
Yes.
Operands for certain built-ins,
right?
Export targets,
and each one maps to an error message.
Comp time known, sentinels. There's all kinds of things there. But yeah, all that is comp time function is doing saying is that non-null. Really straightforward.
So in a sense, the built-in is simple because you have the abstraction, but there is some legwork that needs to be done to keep track if you're in comp time or not.
Yeah, totally. But that tracking is something that we need to do anyway, because we need to know whether we're in a comp time blocked in order to know how to do all kinds of things. Like when we see a function call, we need to know whether we're going to evaluate it at comp time. If we see something that has to happen at runtime, we need to know whether to omit a compile error or not, because if we're in a comp time scope, that's an error.
Yeah.
Things like that. Okay. But anyway, if we go back to analyze body inner, which if you remember is the big old loop, we're looking for mul. So here we are.
Let's go.
This is actually another of those ones that doesn't have its own function. It's in this big old function called arithmetic, which we can take a look at. Now, this function is massive. It's great demonstration. I'm like huge. My point is more that the kind of sequence of things that it does, like through the call stack, is like there's a lot going on here. Directly, it's just calling into this function analyze arithmetic. But actually, we can quickly look at what's going on here first. So this here, you can ignore. It's in a few random functions in SEMA. It's profiling for integration with Tracy. Yeah, profiling. Basically, no one uses this. I think I'm the only person who's used it in like a year. This is the interesting. This is a bit more interesting. So SEMA.code. Code here is the ZIR. That's just what that field is called. If I go to the top of this file, we can see here code ZIR. Instructions, items, data. So understanding this means we need to look a tiny little bit at how ZIR works. So you have instructions, which is a multi-array list of these ints. I'm going to just sort of assume that people in the chat know what a multi-array list is or can explain it to one another. And instructions consist of a tag, which is 1 byte, as we briefly talked about earlier, and some data. And that data is a plain old union of a bunch of different things. The data is going to be 8 bytes long, at least in a release build. And there are like a bunch of different things we can store. So for instance, unnode means we have a source node for a source location, and we have one operand. So the un is unary. The operand here is a ref, which is a term you will remember from AIR a few minutes ago. We have the exact same thing in ZIR. So where you saw like a operand going into an instruction, where we looked at ZIR, where it might have been like in reference to another instruction with the % sign, or it might have been like a constant value with at. That's the same thing. So we're again using we actually don't have the like high bit tag thing here because of just differences with how we interact with the pipeline. But it's the same idea. We have all of these special constant values, and these are all the ones that start with at. Otherwise, it refers to an instruction using %. Yes, yeah. I know Loris knows all this, but I figure let's not leave everyone else in the dark. Oh, well, I guess you'd know as well.
Yeah. So U29, I think it's a special type because that's the size of a Unicode rune, right?
Yes, correct.
And people say that Zig doesn't have Unicode support in the compiler. Checkmate atheists.
We optimize for Unicode code point representation. There you go. We save like a whole ZIR instruction. U21 is Unicode, not... Am I getting mixed up? Yes, sorry. U29 was different. U29 is how we used to represent alignment. Yes.
Oh, interesting. Sorry.
Nowadays, we don't do that because we now represent alignment as the log base 2 of the alignment. But back before we did that, we used U29. Yeah. Sorry, I got that mixed up.
Okay.
Yeah, so I'm pretty sure incidentally we could probably delete this now because it's basically never used. But yeah.
Yeah. So never mind. No Unicode support in the compiler. RIP language.
I'll change it to U21 and then we can claim to support Unicode. But anyway, the point is, there are all of these possible ways to store data. And then there are also these ones, for instance, PL node. So PL here is payload, which means that we actually need more than the 8 bytes of data here. So we're going to use 4 of those bytes to index into another array, which is going to contain the data that we're actually looking for, which can be as long as we want. If you want to understand that stuff more, watch my talk from Software You Can Love 2024. Yeah, so essentially, each of these handling functions is going to need to pull out data from one of these fields. Yep. Okay, so going back here, we are, in this case, going to be using PL node. PL node is, I think, probably the most common ZIR data field. It's used very frequently. I mean, most common in terms of how many instructions use it, or like how many instruction tags use it. But yeah, we want to pull out that data. And then we still have a bit more work to do because we know the index of a payload, but we haven't actually got that payload out yet. So we'll get that payload out a few lines later here using the extra data function. Again, Loris is going to be familiar with this, but this is just a function which looks into the big array, which we have an index into, and pulls out a few elements and packs them together into a struct. In this case, this struct called bin. So this means that this would be a binary operator. So we're expecting the extra array to have 2, it's actually going to be 2 refs in this case, because they might be any values, right? They might be other instructions, or they might be just like plain old 0. So we can find bin here. You can see it's just LHS and RHS. Pretty straightforward. So the long and short of it is that this function call is going to give us out this bin. And so that gives us an LHS and RHS, which are both 0fs. A thing I skipped over here is these 3 calls. These are building up source locations. If any compile errors happen, we want to know, like we want to have the location where it was stored so we can report it against the right location. Unless you're worrying about compile errors, though, you can ignore those. They don't matter to you. And in this case, we're neither getting a compile error nor are we expecting a compile error. So we don't care about them. We'll skip past that. Okay. Now, the next thing we're going to do, we have like LHS, which is a 0inst ref. We have RHS, which is a 0inst ref. Yeah. The problem is that's not enough yet. Like, we know this tells us that, for instance, the left-hand side was a different ZIR instruction, but we want to know what the result was of actually evaluating or analyzing that instruction.
Yeah, there might be a lot of interaction there. There might be a bunch of things, right? They need to be unwrapped before you get to a usable result.
Well, we know that the LHS is already going to have been evaluated because that instruction is going to have come beforehand.
Right.
But the result of that instruction, for instance, it might be a comp time known value, or it might be a reference to a runtime instruction, so a reference to an ARR instruction.
Okay.
But we have a thing that represents either a runtime known instruction or a comp time known value. That's an AIR ref.
Right.
So what we want to do,
okay, that makes sense,
is turn this into an AIR ref. So we tell SEMA, okay, I'm referencing this ZIR instruction. I want to know what the result was of you looking at that instruction. And that's what this function does, resolve inst. Incidentally, this actually doesn't return any errors anymore, I think. I think it's an empty error set. Yeah, it used to return an error because reasons, but I changed it like a week ago and didn't realize that it can't return an error now. But it's actually really simple. We basically just have this map in SEMA, which is, just mapping from 0 instructions to the AIR refs they resulted in. It's not literally a hash map. We have a slightly more optimal thing, or like optimized representation that saves memory, but yeah.
Oh, that makes perfect sense.
And these, like for the special values at the start, they're all in the same order, so we just like convert the enums. Okay, so now what we have is 2 air-inst refs rather than 0-inst refs. So that's great. We know what the inputs are to our arithmetic. They might be comp time known, they might be runtime known. We know the source locations. So now it's time to actually try and do that arithmetic, essentially. So that's what this function analyze arithmetic is going to do. Analyze arithmetic. Cool. Okay.
Yeah.
This function is quite large, but that's fine because it's just, there's a lot of conditionals in there. Most of it we don't care that much about.
Mm-hmm. So, by the way, for people watching, that maybe just to make it clear, what you're looking at is basically, if your question is, wait, how does comp time get analyzed? Like people ask the question, like, is it a bytecode interpreter? No, this is it. This is how it's doing it. Like here, depending on whether the LHS and the RHS and other conditions, depending on how these things are done, then SEMA will be able to immediately resolve everything, or instead output, I guess, another runtime instruction.
I am interested, Loris, in the fact that you said, is it a bytecode interpreter? No. Because what do you think a bytecode interpreter is? ZIR is a bytecode.
I think that when people ask you if it's a bytecode interpreter, I think they imagine that you first output. I think they imagine it in a different way. I might be wrong. I'm sure it does match description to some degree, but I do think that people think that like you produce, like Python bytecode files, that you have a Python style interpreter that interprets it, that kind of stuff. While here it's like much more intertwined. I feel.
Fair, yeah. Yeah, Zig does necessarily kind of intertwine comp time logic and type checking, like they are the same thing. But yeah, essentially, honestly, the way I think of the compiler front end is that it is a big Zig interpreter. That's essentially what's going on here. It's just that sometimes we can't interpret this. We don't know what the answer is because it requires some inline assembly. So we'll just actually just emit some runtime code instead, and that can happen later. SEMA essentially is an interpreter for Zig, which is kind of interesting.
Yeah.
But anyway, okay, we're going to grab some things first. These lines aren't that important. They're just aliases for common bits of state. So PT stands for per thread. ZQ stands for Zig compilation unit. These are just objects, pointers to things that we are going to we're going to need to pass them to a lot of utility functions because they contain references to a lot of global state. We don't need to worry too much about what that state is right now. It's just handy to alias them, and can improve performance slightly because it means the optimizer doesn't need to figure out that they don't change. So yeah. Okay. Next, we know what the LHS and RHS values or runtime instructions are, but we need to know what their types are. So there's this handy dandy function type of. Very simple. Takes in an air ref and spits out a type. I will talk about how types work. Actually, I'll talk about how types work now. So I mentioned the intern pool as this thing that we use to store all our comp time known values, stuff like that. So if we look in the intern pool, this file is really complicated because Jacob is incredibly smart and made a very nice sharded lock data structure, which minimizes contention when we thread the compiler in certain ways. But essentially, the main interesting thing for us is this function index to key. So every comp time known value is represented through one of these intern pool.index values here, which ignore the comment, it's frankly a bit outdated. But you can see it contains all of those special indices again. This is actually kind of the authoritative place for those, I guess. But then, obviously, it's a non-exhaustive enum. And then all of these extra values, rather than referring to, as they do in ZIR, referring to different instructions, these just refer to other values. So every value has one index and one index only. It's through a process called interning.
Yeah.
And so, yeah, any value we represent internally using one of these 32-bit indices. But that's not very helpful. If I just give you the index 8174, then you don't know what that means. So we need a way to convert that into something that the compiler can work with. So that's where this function comes in, index to key. So it takes in one of those indices, which is just an opaque number, and it gives you back one of these keys. A key is a plain old tagged union, nice and simple, of all the possible values we might have. This includes types, because obviously in Zig, types are values, just with the type. So for instance, a value might be an integer type, or it might be a pointer, or an array. And if we scroll past all the types, okay, it might be the value undefined. It might be, ignore those two, they're weird. It might be one of a few sort of special values that we just have names for. Simple value, like untyped things, or it might be the void value, which you write like that, or empty tuple, or true or false, which are special because they're the only possible booleans. So there are a few just like special ones, but then it might be.
Andrew in chat is asking a question for the C++ and Rust people in chat. So you cannot have more than 2 to the 32 types?
That's true. You also can't have more than 2 to the 32 values in a single compilation.
So C++ programmer and functional programmers destroyed by that statement.
I don't think they tend to hit 4 billion types. So this is the ludicrous thing, is C++ doesn't have that many types involved. It just evaluates all that code 12 billion times during
it's just
compilation.
Yeah.
There's something. Yeah, exactly. There is something wrong if a project has 2 to the 32 types. But yeah, the value we have might be an integer or an error union, an enum literal, kinds of things it could be. This just unpacks that information for us into something we can work with. And okay, so if we go back to SEMA, where were we? Yes, so we get these 2 types. These are so logically you'd think they're intern pool.index, and they essentially are. But what we actually use is we have this little wrapper thing called type, which stores an intern pool index. It's just a little struct wrapping it. But it just provides a bunch of methods which make it more convenient to work with, assuming that this thing is a type specifically. So like there's this is self-comparable thing, which is to do with when you write like equality comparisons in Zig. There's like where you can ask whether a pointer type is mutable. You can like ask it to actually like print a value out as best as it can. All kinds of stuff. But the one we're interested in immediately is this function up here, Zig type tag. This is a really important function, actually. The thing it returns is, if anyone who's written a reasonable amount of Zig will be familiar with this, this thing here, standard.builtin.type, which is the way you manipulate and reflect on types at compile time. We can't actually have the compiler work with these directly because like it needs to work with its representation of types. But what it can work with is these things right here. These here, the tags. We can say which of these it is. Is it a type? Is it the void type? Is it a comp time float? Is it an array? And that's often a really helpful way to start some logic, because if you take, for instance, an addition operator, then what you can do is you can say, okay, is this an int? If so, go down this code path. And a float, go here. Comp time in, comp time float, do these things. Otherwise, this is an error, spit out a compile error. So it's a really good way of doing kind of refining types very broadly. Does that make sense? Yeah. So the thing we're going to do here right after we get the types of, so just to remind us, we're currently looking at this.
Yeah. So basically LHS type can be F32, F64, I27, or let's do integers for a moment. So it's going to be like there can be a plenty of integer types that it could be, but the kind is going to be integer, and that's what LHS Zig type tag gives you.
Exactly, yes. So those 2 things are what we're going to get here. we call Zig type tag on the LHS type and the RHS type, and we get the tags. Okay, great. So what's next? Next, we call this thing check vectorizable binary operands. This is, I always kind of forget what this does. I know vaguely. I think it's just, sorry, I'm just skimming this. Yeah, so basically what this is doing is it's checking, it's saying that if one of these things is a vector, then the other needs to be a vector as well.
Mm-hmm.
So let's make sure that they are either neither vectors or they are both vectors. And if not, and also if they are vectors, let's make sure they have the same length. If any of those things don't match, we'll throw a compile error. This is just its own function because it's a thing that essentially any operation that works on vectors is going to want to check this. So it's just helpful.
Mm-hmm.
So let's go back to analyze arithmetic.
Oh,
so it's doing this.
By the way, in the meantime, I'm like, there's like a couple of funny stories from people. So Dax says, I once ran into a problem with that the Java class loader can't load more than 48,000 classes.
Oh God!
Likely, you can start up several class loaders per JVM. So problem solved, I guess. And Scott says, at work, we hit the 16-bit limit for something related to class size or function size due to a very large enum. Wait, which language is that though? Is that like C++? I'm assuming C++ because I know that your company uses a lot of C++, but let's see. It caused a minor emergency. Not fixing it would have blocked our entire large team from adding any features. Wow.
That's pretty wild. Andrew asks how error handling works. Do you mean like how the compiler deals with compile errors? If so, we can absolutely look at that, but we should look at that a little bit later.
Yeah, I mean, you can see some of it already. Like when you see SEMA.fail, also down below, Lugg was showing earlier in the other function, I think he was showing a function to add notes that adds lines that says note this, note that. So you can see some of that. By the way, if you want I don't know if it's a one-to-one, but it's very similar to also what I ended up doing in Super HTML. So if you want an example of probably a simpler, crappier version of what's in the Z compiler, take a look at Super HTML, like the template engine. You will probably see a similar pattern there. Oh, it was still Java. Okay, so I'm sorry, Scott. You should have spun up more function body loaders or something. I don't know. Okay, sorry. Let's go back to the main thing.
Sure. Okay. So, we've done just some checks to make sure vector lengths match. This isn't giving us any result or anything.
Right.
It's just
it doesn't give you any result. It doesn't modify anything. So it just errors out in case something went wrong. So we pass that so we can ignore it.
So yeah, we don't need to pay too much attention to that. It's not important. Okay, we have a conditional. If the left-hand side is a pointer, okay, so this is going to be a branch that's dealing with pointer arithmetic, because you can do pointer plus integer, you can do pointer minus integer, you can do pointer minus pointer. We're not worried about that. We know the LHS definitely isn't a pointer, so we can just skip straight past this whole if block.
Mm-hmm.
Not even going to read it, just go straight to the end. Cool. Okay. So now it looks like what we're doing is we're putting the instructions into a slice. One sec. I'm going to write this how a normal person would write it. There. We're putting the left-hand side and right-hand side refs into a slice. The reason we're doing that is it looks like we're going to call this function, which seems to want them in a slice. It's taking these instructions here. This function is called resolve peer types. Sorry, I'm just fixing this stupidity. Old code from before Zig, from before type inference worked properly. Resolve peer types. So, you familiar with peer type resolution, Loris?
I am. I think probably the audience is also mostly.
I'm guessing most of the audience is. I'll quickly go over it. Essentially, if you do, So the kind of purest form of peer type resolution is if I write const A equals if foo B else C, if B is, say, a U32 and C is a U64, then what type should A have is our question here. And in this case, the answer the compiler will give is U64. What it does to figure that out is it looks at these two types and it says, okay, what makes sense as sort of a common type that both of them can convert to without losing any data? Oh yeah, Andrew's linked.
Yeah, I think people also remember back when this stuff wasn't working properly, and if you had like a constant in one of your branches of the if expression, you had to use as.
That wasn't to do with peer type resolution. That was to do with result types.
Okay.
Yeah. But yeah, so this is kind of the purest form, but peer type resolution is also used when you're doing arithmetic in a lot of cases. So it will say, okay, these two things, they're both integers, but they're different integers. Let's turn them into the same type of integer first, and then we can do the work on that. We don't need to worry about having two different types confusing us. Okay. Well, do we care about that here? Because the thing is, if we go back to our repro, say here, the left-hand side is an F32, the right-hand side is an F32. Down here, the left is a vector of one F32, the right's a vector of one F32.
Yeah.
We know that those types are already the same. So, I mean, we can say pretty much with certainty that unless something's very wrong, peer type resolution is just going to give us that same type out. So actually, we don't really care about this call. We could go in and read the peer type resolution logic, but I don't think it's really necessary here. We know what this is going to be.
Yeah.
So we can, again, I hope it can work on vectors sometime, but vector plus tuple. I want to delete peer type resolution from the language mostly. I have an issue for this, but are we looking for a bug? There is a bug, and I am teaching Loris how to debug it.
Yeah.
The bug is issue 22743 here. It's a nice, simple front-end bug to introduce Loris to his new career as a Zig compiler developer. Okay, so yes, the point is we know that this type is going to be, in the case that we're worried about, it's going to be vector of one F32. So that's fine. We can skip straight past this function call. For the record, this override thing is just to do with providing source locations for each pair, so it can give better error messages if there's not a good type, if there's not a good way to combine the types. Okay. Next thing we're going to do is we have the LHS and we have the RHS, and we have a new type that we want to turn them into. We need to actually turn them into that type. So that we're going to call coerce. Coerce is doing, well, coercion, the same thing as does, the same thing that doing this does. In this case, we know, we just discussed this, that this type is only going to be the same type as the LHS and RHS. So we know the coercion is going to work. Can you guess what the return type of coerce is? This is a little test.
Air reference?
Yes, exactly. Because again, it's going to return, like we're giving it in a comp time known value or an instruction or a runtime instruction. And the result of coercion is going to be, again, like it's a value which may or may not be comp time known.
So I'm guessing that in this case, it's basically an op. Does it return you the same LHS back?
Yeah, exactly.
Because it does nothing, right?
We can quickly read the logic for this.
Yeah.
I never use tabs in Vim because I don't really need to, because I have my normal font size is around this. But unfortunately that's not legible for you.
Yeah, sorry. Part of the problem is that also your screen is embedded, not full screen, to make space for our faces.
Yeah. Okay. So we can look at the function coerce. It actually just calls coerce extra, which is a thing that lets you pass a few more options. So if we look at coerce extra, we ignore that for a second because that's something else that we need not worry about at the minute. These are just more aliases, like we talked about earlier. We get again, aliasing some things. We do a little bit of type resolution, and then we say, if the type is already what we expect, return the input.
Yeah. And I'm
So-
guessing sometimes some coercions require basically no work because I guess it's just a change of type. And some other times there might be some runtime work that needs to be done to execute the coercion.
Yeah, exactly right. So, for instance, if you are coercing something like a pointer to U8 to like an optional pointer to U8, these have the exact same layout in memory. So this coercion doesn't actually require any real work. Yeah. That's actually a special thing that we call an in-memory coercion, but we can look at that far later. That's a whole other thing. But yeah, the point is that we know this branch is going to be what's hit here, so we're happy.
Yeah.
Okay, so the result of that is casted LHS and casted RHS. Cool. What are we going to do next? Well, okay, we're calling this scalar type function. So the idea here is that currently resol type might look like F32, or it might look like some vector of F32. What we want to do is to get this type in either case. So kind of, if it's a vector, look inside that vector.
Yeah.
And because that's a quite common thing, we have a little utility function for it called scalar type. So we can look at the implementation here. Actually, it's really lovely and simple. It takes in a type. Ziku, as I mentioned, is one of these things that just contains a lot of global state. Specifically, the point here is it contains the whole intern pool state. So we'll be passing around references to that quite frequently. But we're going to look at the type tag of this type. And we're going to say, if it's a vector, then we actually want to return the child type, which this is a separate function which does its own thing. Otherwise, return the type unmodified. Making sense?
Yeah.
So, okay, we can say we're passing, we know that like resolved type is going to be vector of 1F32 in the example we're looking at. So then scalar type is going to be
F32.
Yeah, exactly. Cool. Then what are we doing next? We're actually looking at the tag of that type. So scalar
that's
tag.
Float.
Yeah, exactly. Is float. Okay. So this is kind of the information we have so far. We can actually sort of keep this with us and remember some information as we go. Is int, well, okay. Is the scalar tag int? No. Is it comp time int? No, it's float. So is int is false. Cool. Check arithmetic op. I have no memory of what this does. Go on.
Andrew's asking, wait, what's tag? That's what Matt was explaining earlier. It's basically the wider categorization of types. It's what I described as the kind is what you get from when you do when you do type info. So float 32, float 64, float 80, they're all floats. Int, U32, U27, I59, they're all ints.
Yeah, it's so it's exactly this enum. Like literally, we reference standard.builtin.type to get it. So we're just saying what kind of category of type is it. We don't care about specifics right now. We're just trying to classify it. So yeah. Okay, check arithmetic op. I have no memory of what this does. Let's find out.
This looks another thing that either errors out or does nothing.
Yeah, probably. Check arithmetic op. Oh, this is really simple. Okay. We say, is the scalar tag an int or an int? Is it a float? And we say, if it's not an int and it's not a float where a float is allowed, then we error. We could look more at the implementation of this, but again, we know we're not getting an error and we're not expecting one. So I don't really care. We'll just close this. I'm happy to just say we're getting past that, so that's working as expected. Okay. Now is where we're getting to, I think, a big switch. So let me just put this here. I'd like to take this into my selection, and we can bring it back later. So we have a big label block here, which is going to return 3 results, actually. It's going to return a runtime source, which I'll explain in just a moment, an AIR tag, and the AIR tag safe. So, okay, what's going on here is that what we're going to do in this block is we're going to say, can we do this operation at comp time? Or rather, do we know the result at comp time? If so, we're just going to return it here and now straight away. Like figure out that result, return it. Otherwise, we're going to need to emit a runtime instruction, right? And so what we're saying is this is the tag that instruction is going to have. And we know it's going to be a binary operator, so we know what data is put in it, and the tag is variable. And if we have runtime safety, then we should use this tag instead. So for instance,
I see.
Yeah, so there are two AR tags, for instance, for addition. There is add and there's add safe. And safe will cause the backend to include the safety check as well.
Okay.
And runtime.
So to be clear, AirTag is the operation itself, and then AirTag safe is another operation that guarantees safety.
Yeah, exactly. Right. So so AIR instructions are pretty much, they work incredibly similarly to ZIR instructions. We have a big EM of tags, and then we have 8 bytes of data.
Yeah.
And the tags in this case, so for instance, for addition, there's this add tag and there's this add safe tag. And the only difference between the two is that if the code generator sees this one, then it will first do a safety check. So it will say, would this addition overflow?
Oh, I see. Okay, I get it. So okay, because the way I was the reason why I was asking is because I was trying to understand if it's going to be like add safe, or if it's going to be like add and then I don't know, like check for overflow. So it's not the second case; it's the first case. I guess my question then is, why do you do both?
As in, like, why does this block return both tags?
Yeah, why do you not like return the safe one when you're building with safe mode on, and return the other one when in the other case?
It's literally just a property of how this code is structured. We're only going to actually use one of these tags in the code following this block. It's just slightly easier to write this big switch statement but by just returning both and then selecting the one afterwards.
I understood.
Literally just to avoid repeating a conditional n times. Very simple, like no fundamental reason.
Okay.
In fact, we're probably hoping that the optimizer will turn it into the thing you were thinking, where we check the condition inside of it. So yeah, it's worth noting that this is how safety checks generally should work. However, there are lots of safety checks right now where SEMA actually emits some quite complicated AIR to do the check itself. So for instance, if we didn't have add safe, then SEMA might actually emit runtime code which says, okay, I don't know, however you want to do a check, like
do the actual overflow check.
Yeah, do the actual comparisons and then do some Boolean logic to figure out if it's okay, and if not, emit a call to this function.
Was this the discussion about what to have SEMA do versus what to have the backends do?
Exactly. So the way it works with like having separate safe instructions is actually how it originally worked in the Bootstrap compiler. And then when Andrew started doing work on the self-hosted compiler, he decided it should work the other way, where SEMA emits all of the code itself. The idea there is that it avoids code duplication, because it means that you don't need to have every single backend know how to emit these checks. However, that decision was actually reversed. The reason being that SEMA is the bottleneck of the compiler, and it's always going to be the bottleneck of the compiler because it's quite difficult to parallelize heavily. For instance, code generation is like embarrassingly parallel because you just generate each function on a different thread, for instance.
Yeah.
Whereas semantic analysis, you can do that to a point, but always going to be the most difficult thing to do in parallel.
I would also be curious if maybe there could be some architectures where doing the check is significantly different than other architectures.
Oh yeah, absolutely. You can. Like the other advantage of having the specific instructions is that our backends can optimize, can like emit more concise machine code in certain cases. which is, helpful, good thing. But yeah, the downside of it is that we do kind of have to duplicate logic between backends. But yeah, the point is, add safe is the instruction we would omit if we were trying to do an addition, but runtime safety was on. Makes sense?
Perfect sense.
Cool. Runtime source here is, so remember how I mentioned that if we're breaking from this block, we are definitely doing the operation at runtime, like we're omitting an AR instruction. So all this is it's the source location that caused this operation to be runtime. So it's like either the LHS source or the RHS source. If the LHS was runtime known, it's the LHS. Yeah. The reason being that if we're in a comp time block and we can't do this operation,
we complain, we blame it on that thing.
Exactly. Funny enough, we probably will delete this one eventually, because it's actually allowed to do a lot of operations at runtime in comp time blocks, because strange reasons that we need not concern ourselves with. But yeah, that's the idea behind this right now. Okay. So what we're going to do inside this big block is switch on zir tag. This is a variable we didn't talk about earlier. It was actually passed as an argument here. All the way up here was passed as an argument to analyze arithmetic. We know that we were called by zir arithmetic. Oh, look, it's actually passed as zir arithmetic as well, which is passing it through. So if we go all the way back up to analyze body inner and we look at mul, okay, we can see that it's passing mul. So this is just its way of differentiating what arithmetic operation we're doing. Okay, that makes sense. So we're expecting to see mul somewhere in this big switch. And that's the case we're interested in. Make sense?
Yeah.
Cool. Okay, so let's look at the cases. This is add. Well, I don't care about add. We're not doing an addition. Skip that. Add wrap. We're not doing that. Add sat. We're not doing that. Subtract. We're not doing that. So yeah, this function is, again, just a big blob of cases for most of it.
Yeah.
Mul. Okay, here we are.
Found it.
We found it. So I still have this in my clipboard in case we need it. What do we have here? So big explanation of what's going on. For integers, if either, actually, I don't care about this. We're not doing integers. I'm just going to read the comment about what's happening for floats. If either operand is undefined, the result is undefined. That makes sense. If either operand is infinity and the other is 0, then the result is nan. Yep, that makes sense. And if either operand is nan, the result is nan. Okay.
Somebody. So it's interesting because it is written in the comment, and I guess just this got implemented wrong. So it was clear that was supposed to be the case. Cool.
Yeah. Remember that when you do it on a single scalar value, it's doing what we expect.
Yeah.
Just the vector case that's broken.
Yeah. So it's a branch missing in the vector sub branch.
Yeah. Well, it's probably not so much a branch miss. Oh, it might. We'll see. We'll see. Okay. So let's see what's going on here. I should mention I haven't looked at this code in ages. This may be more complicated than I think. I'm hoping it's not. Okay. So what do we have? Okay. So first we're just going to construct a few values that we're likely to need. So scalar tag, we know we computed this earlier. It's float.
Yeah.
So we know we're in this case. Here we're going to do pt.float value. So PT here is kind of similar to ZQ. It's just another wrap around some global state. What float value is going to do is it's going to put something in the intern pool if necessary and give us back out the index at which we can find it later. Remember that a intern pool index is kind of our authoritative name for a value, including a type.
Yeah.
So here we just want to say, okay, we're going to need the comp time known value 0 of type, in this case, F32. So please intern it if it's not already there and just give me that index. So the type of this is, well, in theory, it would be intern pool.index, but float value, you know how I mentioned earlier, we have the type wrapper for an intern pool.index.
Yeah.
We also have a wrapper called value, which is very similar. It just has, again, a bunch of utility functions for various things you might want to do.
Mm-hmm.
So the type of this is actually value.
Okay.
And same thing here, but here we're getting a 1 instead of 0, like 1.0. Again, whoops, sorry. This is a value.
Sorry, I answered earlier that the value, that the tag would have been float, but I guess it would be comp time float in this case because it's I think the value in the source code is a literal, right? So
yes, but that's not affecting the type because we've already, if we look at the repro, we are explicitly saying a vector of 1f32. So this is about the type tag. So it's the comp time float type tag. It literally means the type comp time float.
Yeah.
The
Okay.
float type tag includes
I see what you're saying. Yeah, that makes sense.
Yeah.
That makes sense. Wait, so then so was that the original type of the literal comp time float?
So if you look at like this 0 literal here, this starts out as a comp time float, but because we're using it to initialize this vector, it gets turned into an F32. By the time we're doing multiplication, we know that what we'll have is definitely a vector of F32.
Okay.
Make sense?
Yeah, makes sense.
Cool. Okay. So this is interesting. I didn't actually see maybe LHS val being defined. I might have accidentally skipped over that one moment. Wait, what the? Sorry, I'm maybe LHS.
By the way, later I'm gonna try to do go to definition in ZLS. We'll see how that goes.
I accidentally skipped a couple of lines here earlier.
Yeah.
So just before our big switch, we have these resolve value interval calls. Interval is a really stupid thing to be calling here. So pretend it said this. It would do exactly the same thing. So what this is doing is we're saying, okay, we have, like, if you remember, we have like casted LHS is a air-inst ref.
Yeah.
And so this is value, which is maybe comp time known, can't type, maybe runtime known. If it's comp time known, then we're going to want to do some stuff with that. But we need to know whether or not it's comp time known. We could check like the tag bit of the ref directly, but we do this all the time. So we have convenience functions for it. The one we're going to call here is resolve value, which does a few things to do with like 0-bit types. But essentially, the important thing is it takes in a ref and it returns, ignoring the potential error, an optional value. So if this represents a comp time known value, we'll return that. Otherwise, it's null.
Yeah.
Make sense?
Yeah. Let me look at the implementation for a sec. Has one possible value to be interned? Interesting, because I would have expected like a lower than comparison. No, I'm dumb. So you can do a lower than comparison to check if it's one of the like hard-coded enum values, and those would certainly be known at comp time. But then you would have other instructions that you generate, like random numbers that were generated at compile time. So it has to be more complicated than that. Understood?
Exactly. Yeah. To interned is the function that's doing that, that's wrapping that logic for you. You can see it here. It's just like checking a tag bit and doing a conversion.
Okay.
But yeah, so we're calling resolve value. It's going to return null if it's runtime known, or the value if it's comp time known.
Okay.
Cool. So we go back here. So yeah, we have maybe LHS val, maybe RHS value, maybe because these are optional. So let's get down to mul, just after sub rep or something. One more. Down there. Okay, back here. Yeah. So we found our 0, we found our 1. Now we're going to say...
Yeah, so the initial wrapping is just to check if we do actually have the value, and then if we do have the value, then we implement the logic above, like check if it's on def, check if it's none, return the appropriate value.
Yeah. So here we're going to say if we know the LHS at comp time, well, lucky for us, we do. So that's great.
Yeah.
And then we're saying, is the LHS undefined? No, it's not, right? It's a well-defined value. It's nan, but it's well-defined. So it's not undef, not there. So we're going into here. Okay. If the LHS is nan, well, it actually is in the first one, right? And when we're not dealing with a vector, the LHS is nan.
Yeah.
So the result is nan. Okay, that makes sense. But obviously, a vector containing nan is not nan. Vectors are not nan. Vectors are vectors. So we're going to skip that case here. Okay, I think I'm starting to see what might be going on here, because this is probably the case that we kind of need to hit that we're missing, right?
Yeah.
Or rather, we need to hit
there has to
something.
be another thing that checks for
Yeah, there has to be a similar check
nan.
in the vector code.
Yeah.
Okay. Well, let's quickly have a look at this. Compare all with zero SEMA. Oh, God. Okay, let's see what this does. Compare all with zero. So when you have functions in value that have the word SEMA on the end, they are generally very similar to the version that doesn't have SEMA on the end. So you'll see here there's compare all with zero and compare all with zero SEMA. Essentially, the difference is that when you're doing semantic analysis, you call this one instead, and it's allowed to do type resolution if it needs to resolve lazy values. But in this case, we can read the dot comment here. It's the same kind of idea. So, okay, based on the name, we know we're going to be comparing a value with zero, and we have a compare operator. Compare all. So I'm not quite sure what that means. So let's read this. Oh, for vectors, returns true if it's true for all elements. So if I do, for instance, if my value is, vector 1 f32 0, for instance,
that's true.
Then yeah, and if our op was EQ, then this would be true. But if we had a vector of 2 f32 and one of them was 1, then this would now be false, because they're not all equal to 0. Okay, that makes sense.
Right.
Now that we know what's going on, let's just close this for a second and take a look at what's going on here. If the LHS value is equal to 0, well, let's look at our repro again. No, it's not. The LHS is nan. So we know what we're not entering this code. So we can ignore that for the minute.
Yeah.
Okay. So let's just skip straight past that block. Cool. Then, okay, compare all. Sure. So this is a function on SEMA this time. There's not a lot of rhyme or reason for where certain functions are. It can be quite arbitrary. Just ignore the problem. It's fine. Compare all. Okay, looks like it's doing a very similar thing. It's returning true if the comparison is true for all elements. The only difference is that we're comparing two values rather than one value against 0.
Yeah.
Okay, that seems all right. So let's, so what do we actually do here? We're comparing the LHS value to 1. So SEMA.splat here is the name is clearly analogous to the splat operator, right? So this is just going to take like a scalar value and throw it, like repeat it in a vector if necessary.
Yeah.
So, okay, we're comparing the LHS, which remember is a vector of 1 nan, to a vector of a single 1.0, because scalar 1, that value we got earlier. Is it equal? Well, no, clearly not. Nan is not equal to 1. So, okay, we can skip this as well. We know this isn't happening. So we're down here, and now we're out of this whole block for the minute. Okay, that's fine. Now we're going to look at the RHS. We're going to do a lot of similar checks, actually. So let's check the repro to see what's going on. Is the RHS undef? No, it's a vector containing 0. Is it nan? No, it's a vector containing 0. When we do compare all with 0 equal, well, yes, it does indeed like all of the elements are 0. All one element is equal to 0. Okay, so now we've gone into this code and we're saying if we know the LHS value, then what are we doing? Okay, I'm going to close the repro again. So, okay, as a refresher, we're inside this block now.
Yeah.
Do we know the LHS value? Yes, we do. Is the LHS infinity? No, it's not. It's a vector of nan. Okay. Is the result... oh, wait, no, that's L, so we can skip that. Okay. Splat 0, return 0. So there's our problem, right? Yeah. This is the code path that's being hit.
I'm also... Can you scroll up a bit? I'm a bit surprised that the first branch is so much smaller than the second one.
Is it?
Can you scroll up in the comment that explains the expected behavior? You see how it's very symmetrical, right? If either operand is one thing, then the other, blah, blah, blah. It seems to me that then the two checks should be fairly mirrored.
Yeah, I think you're probably right. There are, I think, quite likely to be some other bugs here.
Yeah, so for example, let's check the 0 and infinity case in the first in the first branch of the if, the one that starts by checking LHS.
First branch of the
LHS. Then we do compare with 0. Oh, we do have the infinite check. Okay, we do have the nan check.
Yeah.
Okay. Let's see. If either operands are undefined, the result is undefined. Does it have undefined? Let's see. So if left side is 0, right-hand side is check against nan, is check against inf, but for example, it does not seem to be checked against undef.
Yeah, I think you're right that there are definitely a variety of bugs here. So actually, I think what we may want to do, somewhat excitingly, is rewrite this block entirely, which we can look at doing in a little bit. Before we do that, let's finish stepping through some of the logic here, try and get an understanding of sort of the structure of what we're looking at. So we have a bunch of similar checks for the RHS, which, as you've commented, seems weirdly much longer.
Yeah.
Okay. So what's going on here? We say if we know the if we know the RHS, if the RHS is undefined, then we do certain things. If the RHS is nan, then we're returning this. If the RHS is equal to 0 or is a vector containing all 0, then we return something. We return a bunch of nans or something, or one nan. We return one nan because this is a single infinity. Okay, I've read enough. I don't like this code. I'd quite like to just rewrite this block.
Yeah, I guess the question is the comment fully authoritative? And I know that probably the answer is that sometimes yes, sometimes no. It's not always the case. But if we can trust the code, the comment, then yeah.
Yeah, I think the comment is accurate. And if it's not, then hopefully we will see some failing tests after we change things.
Right. Nice. That makes that makes total sense. Also, there's another, I think, interesting side effect, which is let me think. I think I had it in my mind earlier. That in some cases, if one of the two values is compiled, I guess one reason why it's important to have also both checks, one where you start with LHS and one where you start with RHS, is because you want to do it, like you want this logic to trigger even when one of the two values is runtime known. So like if you have an undefined that is com time known and the other value is runtime known, it doesn't matter, you still do undefined.
Yeah, exactly.
Which is I guess is already maybe even the starting path where optimizations cause surprising behavior when you have UB in your code.
Yeah. So, okay. Should we think about how we're going to write this?
What do you mean? You're gonna rewrite this, right?
Yeah, well, yeah, but you can.
I mean,
you
okay.
can
So
contribute
one thing that
thoughts.
I'm
Okay.
thinking is that if it really should be fully mirrored, then you could probably just write it once and just swap around LHS and RHS.
Yep, I agree. So here's what I'm thinking here is I'm kind of thinking of this as there are three cases. Case one is LHS and the RHS are both runtime.
Mm-hmm.
In this case, we will end up emitting runtime code.
Yeah.
Case two is one of the two is comp time. And case three is LHS and RHS are both comp time.
Yeah.
Okay. This case, really easy. We skip, like in the current code, we skip this block, and we just break with some tags.
Yeah.
Lovely.
This is a nice early return.
Yeah, we totally can early return that, in fact. This case, where they're both comp time, it's actually also not that bad, because what we can do is we can write a function that just takes in two values and does the correct stuff on them and spits out a result value.
Mm-hmm.
And this one, so you can kind of split this into two sub cases where either LHS is comp time known or maybe RHS is comp time known.
Uh-huh. Yeah.
But as you've identified, as far as I can tell completely correctly, as you've correctly identified, these cases are perfectly symmetric. Like, we need to do the exact same thing here. So we can write another function which says, okay, do we have a comp time known result based on just one comp time known operand?
Makes sense.
Okay, cool. So let's do this. We have maybe LHS val, and we have maybe RHS val.
Yeah. I think one thing only, I need a resin break very quickly. Yeah, I need to return some tea to the universe. And maybe get myself more. So shall we take a how long do you want? 5 or 10 minute break?
Let's go 10-minute.
Okay, 10-minute break and then we come back.
Yeah, okay. Let me find my maps there.
Okay. Let's go take the break then. Everybody, we'll be right back. Also, I think I need to move this a little bit. Oh, yeah, that's probably a good idea to move it like this. There we go. Okay, I'll be right back. Okay, I'm back. Where's my partner? I'm the only one in the office right now. Yeah, this detective agency, man, this city. Why use SED Math NaN F128 instead of the type of float? That's a good question. That is indeed a good question. Do we have like? I think we need like an appropriate YouTube video. I mean, I have the noir music, which you know what? This is not bad. This is kind of appropriate. It's like staring at the window outside the detective agency. Thinking about how bleak is life in the city, but how you can find beauty even in all that bleakness. Hey, Stevie. Yeah, we decided to start to open a detective agency. But for now, it's kind of serious. Then once Lugg gives the control to me, it's gonna become something more like Who Framed Roger Rabbit. For those who have seen it. Video about how about making logic gates using only float and NaN and inf. Wow.
Speaking of Lugg.
Hey, welcome back.
Hello. Did you have a good little break?
I did. I opened my bottle of hard liquor and started thinking about, all the love, all the lovers in my past and how now I'm stuck in the detective agency.
Morris, you didn't choose this life. This life chose you.
It did. It certainly did.
So, shall we continue this life?
Yes, let's continue.
Okay.
Yeah.
So, a thing I should mention, which I didn't mention earlier, is why I am actually very certain that we need to write this code differently.
Mm-hmm.
Because what this is currently trying to do is it's trying to sort of compare the whole vector to some things and figure out an answer for the whole vector at once. But we know that that can't be right. Because, for instance, you could have a vector where like one input is NaN and another is a completely reasonable multiplication.
Oh, so you have to mix and match.
Exactly.
So it's going to be like NaN.
We have to do this element by element.
Right.
So that's what gives me certainty that, yeah, we need to write this differently. Okay, that's fine. So here's how I'm going to... Did this just break?
What break?
Oh gosh, what's happening?
I can hear you.
Oh, are we back?
I can hear you. Oh,
okay.
Can you hear me?
I can hear you, yeah. Can you hear me?
Okay, I can hear you. I can see you. Everything is fine on my end.
Everything's fine. I don't know what happened on your side, but for me, the website just turned into empty space with a line of text for a few minutes or for a few seconds.
Oh, like my screen share garbled. It's probably like a lost keyframe, I guess.
Yeah.
I mean, it's peer-to-peer, so you might occasionally get that. Yeah.
It's very possible that I just had my internet drop for a moment. I'm not sure. Anyway.
Mm-hmm.
Yeah. Here's how I think I'm going to do this. I'm going to say if the LHS exists, then if the RHS exists, I can't type. Then I will do something to handle both being comp time known. Here we know that we just know the LHS. So we say if mul has comp time result. So because sometimes we're going to have a comp time known result. For instance, if we're doing undefined multiplied by a runtime known thing, then we know that the result's undefined without looking at the runtime thing. So we may or may not have a comp time result. And so if we do, then we're going to return that result. Otherwise, so we don't know the LHS, we might still know the RHS. And so we're again going to say if mul has comp time result. This is all obviously very pseudocode right now, but just getting the idea across. Then we return that result. And after all this, we're going to say, okay, clearly the result, I'm just going to delete this crap for the minute. We need that. We need to know what the tag is. But otherwise, yeah, we figure out the tag and we do this. We break, which says do this operation at runtime.
Okay.
That vague strategy makes sense?
Yeah. Okay. Yes.
Cool. So, a thing I am just noting is that, yes, there is a compile error case here, which is undefined. Okay. So because we're going to potentially need to omit compile errors, I'm going to put all of these functions just as methods on SEMA rather than on value, because it's not pure computation. We might want to spit out a compile error. So I'm going to write some functions now. I'm going to write... you can be inventive with your names. Let's actually see what exists here. Add... I feel like there might be a other. I thought there was something with this kind of name that did some kind of arithmetic, but maybe not. Okay, yeah. So there's like int sub, for example. Okay, let's do, I don't know, comp time mul. That seems reasonable for now. So I'm going to first handle this case where everything is comp time known. And what arguments am I going to take? So I need just some basic state. I'm going to take SEMA. I'm going to take the block. These are like, we can get the ZQ out of here, which we're going to need to do like certain comparisons. We need the block because if we omit a compile error, we need to pass the block in just because it's necessary for the error reporting to work properly. Okay. What else are we going to have? Well, we're going to have the LHS value, which is a value. We're going to have the RHS, which is, again, a value. Anything else? Well, we're going to need source locations, because if we do a compile error, then we need to know where to do it. So I'm going to have LHS source, which is, which is a lazy source lock. And I'm going to have RHS source. We can talk a bit more about source locations later, but for now, just to take them for granted. This is going to return a compile error or a value. And this is not an optional value because we know that if the operands are comp time known, the result's definitely comp time known.
Yeah.
Okay, cool. Aren't there some... No, there are not really function ordering rules in SEMA. Broadly speaking, like really important stuff is at the top, like main loop, key control flow things, functions that are called all the time are near the top of the file. But really, we don't mind that much. Essentially, how it's structured. Okay, so the thing we need to handle now is that the LHS might be a vector or it might be a scalar.
Yeah.
So let's actually...
Can you do a vector multiplication with a scalar?
No. So they're either both vectors or both scalars.
Right. And that was already checked, I believe.
Yes, correct. We've already checked that. We've already made sure that these both have the exact same type.
Yeah.
So we can actually recover the type from this. We can do LHS val.type of... with Ziku, and this will return a type.
Mm-hmm.
But actually, we already have it, so
Yeah.
let's pop it in. Why not? So now what we want to know is it a vector or is it a scalar? So what I'm going to do is I'm going to switch on the Zig type tag. And so if it's a vector, we're going to have some case. And otherwise, we're going to do something else.
Yeah.
So essentially what we want to do here is if it's a vector, we want to do this like n times, right? We kind of want to loop and do this case. So I'm actually going to add another function. I'm going to call this one comp_time_mul scalar. The only difference between these functions, they're going to have exactly the same arguments, but the difference is this second one is going to say the thing I'm getting in is definitely not a vector. It's definitely like a scalar value, integer or float, I don't mind, but it's not a vector. And so what we can do here in the else case is we can just return SEMA.comp_time_mul scalar, because we know it's not a vector, and we forward all our arguments. Okay, that's nice and straightforward. Vector, and I want to do some kind of loop. So what I'm going to do first, just looking at the arguments I need to pass, SEMA and block are the same. Tie, I'm going to want the element type of the vector. Yeah. So what I'm going to do is I'm going to say elemtie equals tie.child type. So this is just, I think I mentioned it earlier, utility function. So for instance, we're passing in a vector type, we'll get in out the vector's child. Okay. I now want to know how long the vector is, how many elements are in it. So I'm going to do tie. I think we have vector len. Let me double check this. Vector len. Yes, vector len, which just returns U32. Okay. Cool so far. So now I'm going to iterate. I'm going to iterate that many times. And I'll call that capture LMIDX. Now, actually, wait, what am I saying? Okay, well, let's think about what we want to do in this loop first. We want to get the LHS LM, right? So we want to, we have the LHS vector, we want to pull the right element out of that. So there's, this function, lm value. LHS val, lm value. We've already passed val. We need to pass in pt. Oh, we'll alias that and Ziku up the top in a moment. And we have index, which is lmidx. Cool. And this might return an error, so we just try it because it's only an allocator error, nothing weird. An exact same thing for the RHS. Yeah. Let me just alias some things so I don't forget. Cool. Okay. So we have the LHS LM, we have the RHS LM, and then we're going to figure out the result LM by doing this scalar one. Yep. So we're going to try SEMA.comp_time_mul scalar. Block. The type is now the element type. It's the child type we found. We have the LHS LM, the RHS LM. The source locations are the same. We can't really figure out refined source locations with how with how SEMA works. That's fine. It's close enough. Now we have the result LM. Yeah. But now the question is,
I'm missing a container.
What? Sorry.
Now I'm guessing that you need some kind of container, right? You need to create a vector.
So this is what I was going to say. Is what are we going to do with this? Well, we're going to need to put them in some kind of big array, because what we're going to want to do is get all of these elements together and then ask to combine them into a vector value. Yeah. So we're going to say we're going to want to allocate a little bit of memory. For this kind of thing, we tend to use the SEMA's arena allocator. So we're going to do SEMA arena alloc. We'll look at the type in a second, but the length is going to be len. And I'll call this lm vowels. And because it's an arena, we don't need to free anything. Okay. What type is this? Well, because it's representing a comp time known value, do you have any guess?
Because it's representing comp time known value, do you have any guess? No, I don't.
Okay. So
I'm assuming, okay, my guess is that if it's a comp time known value, then you want to put it in the intern pool, I think, at some point. But I don't know how that connects back to what you're doing right now.
So the thing you need to remember is that every comp time known value we have is actually just an index into the intern pool.
Yeah.
They are always in the intern pool. Value is just a neat little wrapper. So and Andrew guessed value, which is nearly right. But value, because it's just a convenience wrapper, it's like a plain old struct. It has ill-defined layout. What we actually store is a bunch of intern pool.index, which is kind of our slightly lower level representation of a value. Making sense?
Yeah.
Okay, cool. So that's what we're going to do. And now, rather than doing a length iteration, let's do lm_vals. Call that result val, and we still have lmidx. I don't need that length anymore. Or I shouldn't call that result val. I should call that result lm. And I can do that. Okay, cool. Tiny little nitpick here. This is returning value, but we need to turn it into an intern pool index. As I mentioned, those are the same thing. So you do that just by calling this toIntern function, which is actually exactly the same as accessing the field here. It just has another assertion in there that the field isn't something bogus. Okay, so now we've done that. We're almost done with this function. Obviously, we'll have to deal with this one in a moment. But the other thing we need to do here is we figured out all of the element values. Now we just need to create the actual result, right? So we need to pack these elements into a vector. When we're constructing a value, most of those functions are in this file called per thread. We have convenience functions for a lot of it. So let's see if there's anything in here. There's nothing called vector. I think, one sec. I genuinely don't remember if we have a function for this. I'm just checking myself. Okay. So in this case, we don't have a convenience function for it. So we're going to use the slightly lower level interface, which is this function called intern. Okay. So you remember we looked at intern pool.key earlier, which we kind of said was you go from the intern pool.index, which is this opaque number, and you convert it to a key, which is like a nice tagged union, this one here. Well, that relationship actually goes both ways. The way we intern values is we say we have one of these keys, and we say, please intern this for us. An intern pool has all the machinery to do that for us. So what we're going to do is we're going to use pt.intern, which is this function here, and it's going to take in a key. Now, the key we want to make a vector, but there isn't actually a specific thing for vector here. We have a slightly bigger thing which covers like all kind of aggregate values. So that's vectors, arrays, and struct values. If I look for aggregate here you go. So aggregate is an instance of struct, array, or vector. Each element is stored as an index. That's great because we've just filled in a bunch of index. In the case of Sentinel, I don't care. We're working with vectors. There are no Sentinels. Okay, so the payload of this is aggregate. So let's start writing this function call pt.intern. We're using the aggregate union field, and then there's going to be some stuff. Let's call this result val. Okay. Are you with me so far? Because I'm getting a bit weirder. Okay, cool.
No, that makes perfect sense. You have to create the final thing that collects everything.
Yeah. Okay. So let's take a look at what we need from aggregate. First thing we need is the type of the aggregate. Well, that makes sense. It's the vector type, right? The one we've been passed in, tie. Except because the intern pool doesn't use the nice type and value wrappers, it uses raw intern pool.index.
You do.
So we need to convert back
to intern.
Yeah. Okay. Next is storage. So what's storage here? Okay, so this has kind of a few different ways we can tell it what elements are in there.
Yeah.
Because for instance, when we're like interning strings, we don't want to have this huge array of 32-bit values where each one actually only represents a byte. So we have a few different strategies. In this case, we are using elms, right? Because we just have a bunch of indices in a row. Well, not in a row, but we have in a row. So our storage is using lms and lmval, right? Because
Yep.
lmval is the array that we filled in here. Okay. So intern is going to return a intern pool.index. So we need to do value.fromInterned, which is just the conversion in the other direction, just turning that into a value because this function returns a value.
Mm-hmm.
And we're going to return that. I will be fancy and use a decal literal. Okay, so that's this function done, I believe. Make sense?
Makes sense, yes.
Good. So that was kind of the easy bit where we don't need to worry about what we actually need to do for multiplying numbers, the weird rules that we need to deal with. So let me go back to analyze arithmetic and find the mul case here. What if I? Okay, so how do we actually do this in the old code? I shouldn't have deleted the old code, frankly, but we should have mul. Wow, okay, there is really nothing there. That's interesting. Sorry, I'm just trying to... Okay, I'm going to cheat and open just like another work tree I have just to see what this code used to be.
Yeah.
Analyze arithmetic mul, because I want to see how we did multiplications where both things were comp time known. Okay, wait. Maybe LHS val, that's this. So we deal with undef. Compare all with 0, not interested. If maybe RHS val, if the RHS is undef. Okay, so it looks like one of the reasons this case was much bigger before is because I think this was also the one that handled the case of both things being comp time known, which is interesting. Okay, so
I mean,
here we are.
To be fair, the one point where it makes sense to break symmetry is the case where both things are are known, because you can put it in either side, and there's no point in duplicating it. To be fair, it's still problematic, I think. But yeah.
So let's get some things that this. We want to take a look at this type. We want to see what kind of thing it is, because we might be working on integers, we might be working on floats.
Yeah.
So I'm going to say int and comp time int are ints, float and comp time float are not ints. Anything else is unreachable. We shouldn't get here for another thing. Because it should be the case that other bits of code beforehand have omitted compile errors for us.
Yeah.
Okay. So now we're going to say if the LHS is undef or the RHS is undef, then if we look up at the comment here...
Yeah, if either is undef, it's undefined.
Then what we need to do... Well, it's undefined in some cases. The thing is, it depends on whether we're dealing with integers or floats. Because if you're dealing with integers, multiplication actually is of undefined is a compile error.
Interesting. Why is it a compile error for integers but not for floats?
It's a compile error for integers because let's say you did as U8 255 times as U8 2. This is illegal behavior, right?
Yeah.
Because it's overflow. Whereas with floats, you can never trigger illegal behavior by doing a multiplication. So if I have like x times y, there are no values I could put into x and y here where this would be illegal behavior at runtime.
Mm-hmm.
But when you have undefined semantically is allowed to be any value.
Mm-hmm.
I mean, even any bit pattern. So if we're doing like undefined times 2, well, we could sort of say that maybe that undefined is 255, in which case that's a problem.
Yeah. Okay, that makes sense.
Technically speaking, there should actually be checks here. I think that because, for instance, I think undef times 0 should actually be okay. However, let's only fix one bug at a time. We can leave that for later.
Yeah.
But okay, so if either one is undef, then if this is an int, then we're going to error, which we'll do in a second. And otherwise, we're going to return undef. Okay?
Yeah.
So let me expand these out. Else, I can't type. Return undef. Okay. So how do we return undef? Well, you know how I mentioned that the per thread type has convenience functions for making certain values?
Yep.
One that it has is this function undef value. So you pass it in a type, and it will give you back an undefined value of that type.
I think above they were using pt.undefref.
Yes. So they are very similar functions. The difference is that value returns a value, whereas ref returns an air.ints.ref. So all ref is doing is wrapping value and doing a conversion. Because if you remember, a ref is either a comp time known value or a runtime known value. But because here we're working completely in comp time known stuff, and we're later going to convert to runtime known, we're later going to convert to refs, I should say. We want to use value here, and we're going to do that conversion a bit later.
Okay.
Does that make sense?
It does. I'm a little bit fuzzy with the details, but it does make sense. I just kind of forgot about all this part when it's been a while.
Yeah, no, it's fair enough.
Yeah. Okay.
So here we want to commit an error because something's undefined. We have a convenience function for this. You can actually see it used here. Fail with use of undef.
Yeah.
So we can take a quick little look at 1732. Let me do a tab new just so we can take a quick look at this. Fail with use of undef. Okay, you can see the error it's going to spit out. Use of undefined value here called undefined behavior. Makes sense. I just thought those should probably say illegal behavior now because we're changing our terminology. But that's an error. That's a problem for another day. Okay, the point is here we're just going to return SEMA.fail with use of undef block. Okay, well, this is interesting. We need to pass in a source location, but that's going to depend which thing was undefined. So actually, perhaps we should split this up a bit. Or how will I write this? This is very bike sheddy. It doesn't matter. Let's just do if LHS val is undef, LHS source, else RHS source. That seems fair enough.
Yeah.
Undef source. Cool. Okay, that's our first case dealt with. I see. So what I missed here is that these are ordered.
Yeah, I realized that as well. Yes. Yeah, there's an order, so we need to start with 0. Well, okay. Not a big deal.
Yeah. Well, let's take a look at float and double check how this works. Okay.
You also need 0 and 1. Maybe you can. I don't know if you should move them or accept them as input. Maybe move them. You remember that you had.
My instinct is that we should actually have completely separate branches in this function for int and float.
Okay, fair.
I think this is going to be a nice way to write it.
Yeah, the rules are sufficiently different, I guess.
Yeah. So what we can do here is we can say if, so for instance, in the float case, we can say if that or that, then we're returning undef value. Cool. And up here, we can have like our 0 and 1 checks first, and then we can say if the LHS is undef, then fail with use of undef block LHS source, and then we can do the same thing for RHS.
Okay.
That's nicer. That's better. Okay. Let's go through the integer case then. If either operand is 0, the result is 0. Sure. So if LHS val dot, okay, I want to check whether this value is equal to 0. You actually saw a bit ago, we have some specific functions for comparing to 0. So we probably want, sorry, I'm just checking whether there's any. fin.star0, because I forget whether there's any other interesting ones. Compare all with 0, order against 0. Okay. They're probably pretty similar. My instinct is probably to use...
The old code had an instance of 0 and an instance of 1.
That's true.
Is that like an old deprecated approach, or?
No, that might be a reasonable approach. Let's actually take a quick little gander at how this... I'd say there are advantages and disadvantages to that approach. Sorry, I'm just trying to think this through.
Yeah.
My suspicion is that that approach is faster for big vectors and a bit slower in the common case. But that might be wrong. The reason that the way order against 0 works is it's doing an index to key on the value and then checking the storage directly, which is a fairly fast operation, but it's not as fast as like a plain old comparison of intern pool index. Whereas like interning the value 0 will take a little bit longer, but you can then, if you're doing if you have a really big vector and you're going to be comparing loads of stuff, then that kind of offset that cost, right? Because then that comparison becomes really cheap.
Mm-hmm.
I'm going to say, just to simplify these functions so that I don't need to pass more arguments between them, I'm going to use order against 0.
Okay.
Or possibly compare hetero. That might be better. Do you know what? No, you're right. You're right. I should totally be creating 0 and 1. So let's have. Nope, I'm overruling myself for like the 5th time. I'm going to do compare hetero. Compare hetero is nice because it doesn't give a shit about types. It's a quite loosey-goosey comparison function, which works just as well. So it makes it very easy for me to do, okay, if the LHS, because I'm just thinking about the fact that after this I'm going to want to compare to 1, which obviously we don't have a special function for. So if it's equal to 0, and the nice thing is that because compare hetero doesn't care about types being equal, I can just give it 0. Like this is one of those special constant values.
Mm-hmm. Oh, you don't need to create a typed 0 that matches the type.
Exactly. I don't need to make a type 0. This is just 0 as a comp time int, and that works fine.
Okay.
Right, compare hetero to 0. Oh, my monitor's off again, but I think it'll fix itself in a second. This might just be a dodgy power cable. Let me wiggle some stuff a bit.
Mm-hmm. Well, you're still online.
I know. I'm pretty confident this is just something wrong with the power cable or something. That said, it doesn't seem to want to turn back on this time. Let me try a different plug on this power strip. Sorry about the technical difficulties.
No worries.
Oh, okay. Wait, I think we're getting power again.
Back in business.
We need to wait a second while the monitor actually turns on. Okay, we're back. Sorry about that. Okay, let's compare hetero. I might change my mind on how this works later, but this works for now. Checking whether the LHS equals 0, and we're going to pass Ziku. If either operand is 0, the result's 0. Let's also do the same thing for RHS. Oh, sorry, we should be calling compare hetero SEMA here for the reasons I mentioned earlier.
Yeah, to trigger lazy evaluation.
Yeah, exactly. So, or try RHS val EQ 0 Ziku. So, okay, if either thing is 0, what are we doing? We're returning 0. Okay. So there is, again, another helper thing, int value, where I can say I want 0 of this type, and it will do that for me. Okay. And then I want to check if either thing is 1. Sure. So we can basically take this exact same code, but do 1 there.
Out of curiosity, why not return LHS, for example?
No reason, honestly. That would work completely fine.
Okay.
Yeah, that. Oh, so wait, I just realized this is not actually what I want. This is actually the wrong thing here. I need to return the other operand. This is not how multiplication works. But yeah, for this one, for instance, I could totally return LHS val.
Okay.
If that was 0, or RHS val if that was 0. I prefer doing this because realistically, the performance cost is completely negligible, and I find it more readable.
Understood.
But yeah, it would be completely valid to split this into 2 ifs. Say, like the first one here, return LHS val, then the second one return RHS val. That would be fine.
Okay.
It's kind of just a matter of preference. However, this one does need to be 2 conditionals because here we actually do need to return the other value, right?
Yeah.
Multiplying by 1, that's how that works. Okay. Making sense?
Yep.
Cool. Okay, so we've dealt with that. We've dealt with that. Even if it's undefined, yep. Either is undefined, that's a compile error. Yep, we've done that there because there's possible value for which the addition would overflow.
Yeah,
right?
By the way, you mentioned it. This is interesting. That what were you saying earlier? That undefined. No, never mind. This also covers, like, the 0 case also covers the case where the other one either is undefined. It only matters is that one of them is 0. Yeah, so
Right,
it's just not written explicitly in the comment. Okay, yeah.
Yeah. Okay, so we've now dealt with all the special cases, and we just need to do actually multiplying integers. And it looks like if we look back at the old code here, there is a function that does that for us, which is good because that would be a really annoying bit of code to write. Because we'd have to deal with it potentially being a big int, or maybe one thing being a big int and one thing being represented more efficiently. There's a lot of cases to handle, but it's been done for us. So we're going to say product. So actually, this is interesting. This function lets us pass in an overflow index, and it will tell us if we have an integer overflow. That's quite nice. So, sorry. Let's basically nick this. LHS val, int mul, RHS val. We just called that tie, overflow IDX, SEMA arena, PT. That all seems reasonable. And we're then going to say if overflow IDX, vec IDX. So this is telling you like what index into a vector, if applicable. So we do return SEMA fail with, I clicked accidentally, with integer overflow block. What's the source going to be? Well, yeah, this is a good point, actually. We have the LHS and RHS source, but we do need
whose fault is it?
Yeah, because it's neither one's fault. It's their combination. So we need an overall source location as well. That's fine. We will pass it to this as well, and we'll just forward it through. So source goes there, and also goes there. Okay. Where are we? Here, yes. So fail with integer overflow, source, tie, product, vec IDX. I've just copied that straight from over here because I have no reason to doubt that that works fine. And if this wasn't populated, then that means that we got the right result and it had the right type and everything like that. So we can just return product.
Yeah.
Okay, that's the int case handled. So now we need to deal with floats, which frankly looks like it might be a bit easier. So if either is undefined, the result's undefined. Okay, we've dealt with that. If either is infinity and the other is 0, the result is nan. Okay. That's a very specific case, but sure.
Hey, Heisenberg's apprentice, thank you for the $5 to the ZSF. Let's go. Thank you. You're helping the funding the detective agency.
Yeah. 1 second, I'm gonna have a sip of tea, paid for by that $5. Okay, so If either is inf and the other is 0, the result is nan. And if either operand is nan, the result is nan. Sure. I mean, let's deal with either being nan first, because the order of these two doesn't matter, and that seems like it's an easier one. We just say if it is nan or is nan. You know, having said that, is there... We actually might need to specifically return like LHS or RHS val here, because I don't think we have a way to an easy way to construct a nan value. So I'm going to write this like this, and the same for RHS. Make sense?
Yeah.
Okay. And so, right, the remaining check is if one is inf and the other is 0. Sure.
Yeah, by the way, just writing down two ifs, one after the other, one for left, one for right, is like, it's good. Like, it really simplifies otherwise the spaghetti mess that the other code was. Like of the original code, I mean.
Yeah.
Nice.
Yeah, I think we're making a good improvement on the old logic here. Okay, so we want to check one operand is infinity and the other is 0. Okay. So let's say LHS val is inf, and what I really want to write is RHS val is 0. That's not a function that immediately exists, but we can, obviously, we've done stuff like that up there. We can worry about that in a second. Let's just pretend it does exist for now.
Yeah.
Then we're going to want to return nan. Interesting. I wonder how that's implemented in the old code. Maybe we do have a good way of making a nan value. Okay, so we just make a F128 nan, call float value, which is another of those wrappers.
Somebody was asking earlier, why F128?
F128 is the biggest float type Zig supports, and so comp time float, because we want it to be as precise as possible, has the same precision as F128. And so F128 is kind of our default for doing float arithmetic in the compiler, essentially. Someone said, I went to see how errors work, and I saw error comp time return, error comp time breaks, not reg error. We can talk about errors in a little bit.
Yeah.
But I think you got unlucky with where you looked, essentially, because that generally there is another error or two. Okay, so, well, we can actually change this bit then. So we can say if the LHS is nan or the RHS is nan. And we can actually just throw this all, because all of these need to return nan. So let's just throw in a bunch of cases here. LHS is inf, and RHS, again, I'll pretend that is 0 exists for the second.
Nice.
Or
okay.
The LHS is 0, and RHS is inf. Now, according to the comment, we'd be done here. However, there's definitely a case it left out, which is negative infinity. Checked before is not the comment ordering here doesn't matter, because like these cases are mutually exclusive. Like, you can't ever be hitting one then the other. Sorry, one as well as the other.
Is inf does not return true for negative inf?
This is actually a question.
It's calling SED math is inf.
Lib standard math is what did I press? What did I open? Okay. Is inf is in math / is in. Yes, sorry, I think you're right. I think that does return if a negative as well, which is good. Yeah, okay, because there's also a specific like is positive 0 is negative 0. So that's good. Okay, we don't need any other cases. In any of these cases, we are going to return pt.float value tie stud math nan F128. Cool. And what are we going to do otherwise? Otherwise, we're going to actually multiply things. Imagine that. Which the logic for that must be somewhere here.
Float mul? maybe. The other one was int mul.
Float mul. Yeah, here we are.
Yeah.
So we're going to return LHS val dot float mul.
Oh, that's a try
right.
with a parenthesis around it. That's evil.
Because they're doing to intern on the result.
Yeah.
So, float mul RHS val tie arena per thread. Okay. Is 0 here? As far as I'm aware, doesn't exist. I kind of want it to exist. And the thing is, we also need to bear in mind this also needs to check for -0 because floats are weird. I wonder what the comparison functions do for 0. See, the more I look at this old code, the more I'm convinced that it's really horribly broken. Because I don't think it handles a lot of these cases correctly, really. Okay, so it's doing compare all with 0 SEMA. That's interesting. So, okay, do you know what? Let's follow their example for the minute. That's fine. So I'm going to split this back up. I'll do that case first, and then I'll sort of nest some things a little to make this slightly legible. I'll say if the LHS is infinity and try RHS val dot compare all with 0 SEMA EQPT, then we know the LHS was infinity, the RHS was 0, and the same thing but flipped around. So RHS, LHS. Okay. Does this all make sense, what I've done here? I'm both asking in terms of me showing you what I mean and in terms of, is my code correct?
Yeah. So there is one question that I have in my mind reading this, which is that you mentioned on occasion that sometimes you could have values that are not fully evaluated. And so by calling the SEMA variant of a function, you trigger full evaluation.
Yep.
Well, you're allowed to trigger that, right?
Yeah.
So why does that not happen when we're doing NaN checking, for example?
Actually, here, I could get away without calling the SEMA functions. The reason is that in Zig, lazy values are very restricted. The only lazy values we actually have are integers.
Okay.
So you need to call those SEMA functions when you're dealing with integer values. When you're dealing with floats, you actually don't need to. Nothing's going to break if you don't.
Okay.
It will raise a couple of eyebrows if you don't, so probably do it anyway, just in case. But essentially, when we're working in floats, we don't need SEMA variants of these functions because floats never lazy evaluated.
Understood. What about the integer branch above then? Because we ended up, we ended up using compare SEMA pretty much everywhere. Well, we have is and def. What about is and def?
You also can't have lazy undefined values. There are exactly two lazy values in Zig. There is size of t and there is a line of t.
Okay.
These are the only lazy values we have, and they are always well-defined integers.
Okay, understood.
Yeah. What's someone saying? Oh, right. Sorry, that was a comment from earlier. I'm still split on how to write this, but I'm just going to leave it as is for now, because otherwise I'm going to bike shed a really unimportant thing for ages. Okay, so I'm pretty sure this function is done. Comp time mul scalar and by extension comp time mul. So I guess we can quickly hook it up. If we go to analyze arithmetic, we have the mul case here. And
I think we skipped the is 0 comparison. I don't remember if you kept using it. And no, you did compare all with 0. Okay, never mind. Okay, we're good.
Yeah. Okay. So if they're both comp time known, then I'm going to return sema.comptime mul with block. I think it's called resolved type here. Where are we? LHS val, RHS val, source, LHS source, RHS source. Yeah, they're all named the same. I also totally don't need the 0 and 1 here anymore because I'm
Yeah.
doing all this handling elsewhere. Okay, so that's the case where they're both comp time. So, and that's kind of the I was going to say that's the easy case, but actually no, I think it's about as hard as the other one. So now what we need to do is handle the case where one thing was comp time known, but the other was runtime known.
Yeah.
So let's say partial comp time mul. I'm pulling these names out of my arse, by the way. Like there is no real standard here. I think the algs are going to be pretty similar to this, so I'm going to nick them and change them. Block tie LHS val. We don't have an RHS val because that's the whole point. Or well, we also don't know that it's the LHS. We just know that it's the comp time val.
Yeah.
Which I'll actually just call val because otherwise it's going to be annoying to type. And so we have the source of that value. I'm guessing we won't need the source for the one we don't know.
Yeah, you don't, because there cannot be something that is because of both, right?
Yeah, exactly. Compile error bang value. Or, well, the thing is here it's an optional value, right? Because most of the time, if we just have one comp time known operand, we don't know the result.
Right, you want to go...
There are a select few cases where we do.
Right.
Okay. Now, this is the main function where it might be a vector. So actually, it's going to look really similar to this to the extent that I'm going to copy paste this and change it. So I'm going to say, okay, what's the type here? If it's a vector, then we're going to build up our element values, and we're just going to get the val here. So a single lm, and we're going to do partial comp time mul scalar block lm tie. Yes, so we have the lm val, the source, and the val source. Now, this I'm actually going to split this into two lines because maybe lm result I'll call that, because this might be null, right? We might essentially when we're multiplying vectors where we only know one of the vectors at comp time, then we can only give a comp time known result if every single element is going to be comp time known. So for instance, in this case, yeah, we'd know to have a, well, no, that's a terrible example. This is the exact issue we're dealing with. Actually, yeah, if these were integers, actually, then in this case, we would know that we could return.
Wait, so I guess the question is, can you have a vector that is partially where some elements are known at comp time and some are not?
No, you can't. So the Zig has this restriction for simplicity that a value is either fully comp time known or it's not. It's fully runtime known.
Okay.
So the only case where we can actually return a comp time result for vectors here is if we would know every single element. So for instance, in this case, if we're working in integers, well, we know that the results are all going to be 0.
Okay. So okay, the case of zeros. Okay.
Well, it's the cases that are, it's some of the cases that are in the comment here. We'll go through them.
Okay.
So what we have is we have this maybe result, and what I'm going to do is I'm going to say maybe lm result or else return null, right? Because if any single element wasn't known, then the whole thing isn't known.
Yeah.
Okay, cool. So then I'm just going to say this is lm result.toIntern. And then at the end, yeah, I can again just intern the aggregate. This doesn't need to change. Okay? So now I write partial comp time. Oops, sorry, I just realized I've missed. I need to change this. Cool. So it's block tie val source val source. Is that all? Block tie val source. Yeah. Did I accidentally put an extra argument in this one? Or am I? No, it's fine. Okay. Sorry, I confused myself for a second. Okay. partial comp time mul scalar. I'm going to be taking same arguments. It's the same exact thing, just I know that I'm not working on a vector. Okay. I'm going to start this off the same way I started the normal multiplication. I'm going to see whether we're working on ints or floats. Because that's going to decide what checks I do.
Yeah.
Okay. So, if it's an integer, well, if either operand is 0, the result is 0. Okay, so if the value is 0, then we know we have a comp time known result of 0.
Yeah.
Cool. How did I choose to compare to 0 up here? Oh, I've been inconsistent, haven't I? I've done compare all there. Let me be consistent. Let me compare all with 0 SEMA here. I'm sorry, I know I said I wasn't going to fight myself here too much, but I... okay, these two need to be compared hetero because they're comparing to 1. I remember. Okay.
Mm-hmm.
Cool. That's now consistent. Okay, compare all with 0 SEMA. If val dot compare all with 0 SEMA, ZOR 0 EQ ZQ. So if the value is equal to 0, then the result is 0. So as you pointed out, we can just return val here. Let's do that. That's fine. If either operand is 1, the result is the other operand. Well, we don't care about that because that's not a comp time known result, right?
Yeah.
Because if we just know that one operand is 1, then that isn't helpful. Yeah.
Then the value is not fully comp time known.
Exactly. If either operand is undefined, it's a compile error. Well, that's only if either operand is undefined and the... one sec, sorry, my brain is working at full power.
So this is this you want to check because if the the known value element is undefined, then it is undefined.
No, that's not true because this one case kind of guards it. So if we have like comp time known undef,
shit, you're right.
Runtime known 1, that's well defined.
Right. Fuck. Right. So you can say that.
Yeah. So that check we're also skipping. So actually, this is the only.
We're done. Yeah. I guess we're done at this point.
That's all. What did I?
So return null.
No, I totally. Oh fuck. Sorry. I lost where I was. There we are. So yeah, otherwise return null.
Yeah.
That was easy. Okay. What about floats? If either operand is undefined, the result is undefined. That makes sense. If val is undef, return. Again, we can just return val. That's fine. If either is inf and the other is 0, okay, well, that doesn't apply because we need to know both.
Yeah.
If either is nan, the result is nan. Well, I don't think that applies, does it? Because that's going to... Oh, yes, it does. Sorry, because, yeah, the order of these doesn't matter because these can't both be true.
Wait. The question is, can the other runtime value be undefined?
Can the other runtime value be undefined? Ah, that's a good point. Yeah, you're right. You're completely right. So that's the only check we can do at comp time. Because if we codified this thing, then we would have that comp time nan times runtime undef equals nan, which would be wrong.
Mm-hmm.
So you're correct. We just return null here. Okay. Then that's that. To be honest.
Yeah.
Okay. So all we need to do is wire this in here. This function. Try SEMA.partial comp time mul with block resolved type. I just realized this means we don't need the source locations at all, do we? We literally don't use them. Huh, okay. That simplifies this a lot. That goes away. They go away. Yes, so block resolve type LHS val. And same thing here. If try SEMA.partial comp time mul block resolve type RHS val. If this has a comp time known result. Now, currently I'm just writing return result here. That's not quite right. So let me also do that. Because result is a value, we need to turn it into a air ref. Because
Right.
obviously
So you have to
the
do.
function doesn't know whether its return value is necessarily comp time known.
So what is it? Value from something to ref.
So yeah, we need to call two functions.
Oh.
So we need to do take results and turn it into an intern value, into an intern pool index, and then we turn that into a ref. It's a slightly irritating two-step.
No, you're right. So you're unwrapping the struct, getting the number, but then the number needs to be offset to become a ref.
Exactly.
Yeah, I remember.
So we throw that in all three of these places. Okay. Okay. What have I done wrong? Oh, okay. I forgot to write if. Undefined zku. Yep, that's true. PT is sema.pt. Zku is pt.zku. Do I actually use a PT here? I do. Comp time mul scalar. Okay. I think I just need zku here. So sema.pt.zku. Undefined. Oh, wow. Of course, I don't even use block here because I can't compile error. So I need even fewer arguments than I thought.
Man, the beauty of having unused variable errors, huh?
Yeah, it's fantastic. Everyone should have unused variable errors. Okay. Ash check's now happy. Should we try and build this compiler and see what happens?
Let's go.
Apparently I changed something in here. Sorry, I've been changing all kinds of files showing stuff. There we go. Okay, let's clear my screen. And if I go up a few commands, okay, apparently I did more crap than I thought. There we go. Let's do that. It's recompiling the build script because very silly reasons. This was, I will say, I was clearly wrong about the scope of this bug. I thought it was a lot more than it was.
I mean, we found out that there was definitely a bunch of missing stuff. It wasn't just that one case. I mean, that's cool. That was a nice discovery.
Yeah. We'll have to check whether the other one is. How long would you take to fix them both not on stream? I would have. I've seen the compile errors. I'll stop in a sec. If not on stream, that would have taken me 5-10 minutes. It wasn't trivial because I would have done what I just did and rewrote that logic. Yeah, that probably would have been a 5-10 minute job. Okay. Expected. Well, okay, what we can do here, we've got some compile errors to fix, and we might have a few. So what I'm actually going to do is I'm going to use incremental compilation. Okay, let me explain this command. Zig build, obviously building the compiler. No lib, use LVM files. We talked about that earlier. Summary rule, I'm actually going to delete. I don't want that now because that's going to get in the way. Libdir, we talked about. Okay, f incremental. This tells the compiler to enable incremental compilation. Watch, this tells the build system, look at all the files in this project. When I change one of them, rebuild stuff. No bin is telling our build scripts, don't try and output a binary, just do semantic analysis, so like type checking, and we'll get compile errors, but we won't get a binary if it works. That bloody screen's just turned off again. I don't know what's wrong with it. It clearly must be this case. I don't. Apologies for the technical difficulties.
Yeah, don't worry. People are used to this stuff on this stream.
Oh, okay. I figured out which end of the cable is broken, I think. Clearly the plug end, because when I wiggle it wrong, monitor turns off. I have another kettle lead. I should totally just use one of those. Okay, here we are. We're back. So yeah, no bin, telling the compiler, don't output a binary. Two reasons we do this. One is that incremental compilation isn't brilliant at omitting binaries right now. It works in some cases, but you can break it more easily than you can break kind of the front end half of incremental compilation. Second reason is it's faster. It avoids a big chunk of the compiler, so takes less time. So what I can do is I can tell the compiler to do this stuff, and this means that we're going to be able to fix compile errors more quickly because we're going to get pretty much instant feedback, unless my incremental compilation code is bad, which it sometimes is. So it's going to do the initial build, which will take normal amount of time, a good few seconds. In fact, a bit longer than it otherwise would, because incremental compilation has to do a little bit more tracking of some state.
Mm-hmm.
Build on save.
Yo, we have Techatrix. Let's go. Okay. Hey, Techatrix.
So let me close that browser. And let me...
By the way, sorry, everybody. I've not been greeting people because we've been doing actual work for this stream. I know you're not used to this stuff, but sometimes it is what it is.
It's pretty wild, yeah. Okay. Let me go into the same directory and do some editing. So we have an error on line 38881.
I'm surprised. Why do you not... Wait, why do you not do a horizontal split?
I'm
actually curious about this. And also, can you do... you can also do... what's it called? I have it. Prominent compile errors, right? So that way the errors...
Yes, I forgot to do prominent compile errors.
Yeah,
that's the only reason.
Okay, it's fine. Yeah, let's go.
Yeah, horizontal split does make more sense here. Usually I don't do it because I find it less helpful, but when I have this really big font size, yeah, that does make more sense. Okay, so it's complaining that here we expected a per thread and we got a ZQ. Okay, so I clearly just had to pass PT in here, and that's going to be the same thing there. When I save that, there, rebuild.
Holy shit.
Okay. Here,
Holy shit. By the way, people watching, just to be clear, that's the entire compiler that has been reanalyzed. That's the dev loop. That is the development loop. A while ago, let me rant a little bit, Matt. While you do the real work, I do the ranting. A while ago, people kept complaining on Hacker News and similar places that it was the people that, like, the Z project was like expanding the scope for no reason, not focusing on what wasn't strictly necessary, not really trying to go to V1 fast enough, and instead, doing whatever, everything. Like, people donate money and then they waste it on random stuff. No, this is it. This is what makes a difference. You are developing a compiler, and it takes a blink of an eye to get a rebuild. That is the point. I'm not gonna name names, but I do suspect that other projects are genuinely bottlenecked by how long it takes for them to just simply rebuild their thing.
Okay, so I fixed the compile error, so you can see this is now saying success. That last update was 90 milliseconds. Obviously, because I passed no bin, we don't have a binary, so I'm just gonna run this now, and we'll get an actual build of the compiler. I don't know why it keeps rebuilding the build script. That's probably no, I do know why. It's my fault in a sense, but in a much more real sense, it's either Andrew or Jacob's fault. I can explain that later, but it's a weird thing to do with cache invalidation. Okay, so we've now got a second to wait. I'm not going to be surprised if this crashes, by the way. This kind of thing can be surprisingly finicky to get quite right first time. Okay. Bin zig, let's build obj r repro .zig. Oh, has that worked? I think that might have worked.
That is success. Yeah, that's none in both cases. Is there a test suite? Can you isolate a math-related test suite to run?
Well, what we can do is we can do tests. So obviously you're aware that the behavior tests exist, which test all manner of stuff.
Yeah, sure. I totally am.
But what we can do initially is just run the math file in the behavior test, because this compiler is pretty slow.
Jokes aside, I know that the behavior tests exist, but I've never run them myself. So I don't know how you actually run them.
Ignore this. I don't know why I have a lib directory there. There we go. The behavior tests are self-contained. You can literally do like zig test.
Okay, just a single file, one at a time. Okay.
Yeah. Well, it's a bunch of files, but yeah, you can just test a single file. It imports all of them. And in this case, I'm just testing the math stuff because that's where I'm expecting we will probably see errors if there are failures, if there are any.
I mean, we certainly can catch regressions, but the fact that the previous code was there, happily there, it definitely means that there's a ton of behavior that is not
for sure
tested.
Yes. Like the next thing we should do, which is I think the least glamour or at least least fun part of compiler development, is writing tests.
Yeah.
But you need to do it. The rule is whenever you fix a bug, you add a test covering that bug. Yeah. Unless that's like really hard to do for some reason. Like there are occasional edge cases where it's really hard to wire something into the test harness. Okay, so all of the tests in there succeeded.
No regressions.
What? Sorry.
No regressions, man.
Yep.
Nice. Yeah,
first
try.
So far. Let's try some other stuff. Floatop. This is doing some kind of floating point operations, I guess. I don't know. I don't remember these file names for the record. I just sort of guess how I would like categorize the tests. And normally most people's brains work similarly enough to mine that I can figure it out.
Wait, I'm surprised. Float OP is not under math. Also, were vector tests under math. So there is no dedicated vector file, I'm guessing.
There is a vectors file. The categorizations here are really weird because they've just been built up by a variety of contributors over time.
That makes sense.
So, for instance, there are a few hyper-specific files. Like, I think at one point there was one that was testing essentially one specific behavior of patch structs.
Yeah.
Whereas if I was writing that test, it would go in the file structs.zig.
That makes sense. Related, I implemented yesterday snapshot testing for Zine, and like I was thinking at some point, should I like somehow categorize what I'm testing, like which parts of the language templating language I'm testing, and then I said, nah, too complicated. I'm just gonna toss stuff around, and that's gonna be good enough.
Yeah. I figure at this point I may as well run the whole behavior test. It'll take a minute or two to build. Again, this doesn't take long to build if you have like a fast compiler, but because we built this compiler in debug mode using the self-hosted backend, it's not
super debug. Yeah.
Yeah. What I don't know if I need to check whether the compiler is updated to use. No, because it's not in master yet. Because Andrew implemented a new fast allocator recently.
Yeah.
But it's not in master right now. It's in a PR, I believe. And so
what better time to get it in master than 1 week before the release?
Yeah, I think he's doing it though. Yeah, anyway, but the point is that means this is it's using debug allocator, formerly known as general purpose allocator, which is very, very slow. And that contributes a lot to the slowness of this build. Yeah. So what I should have done is when I was building it, I should have passed -d force link libc, which would have made it use the C allocator instead. Yeah. Which would probably half the compilation time here.
Huh.
But we're too far in now. Sunk cost.
That's fair. That's cool. So while we're here, you mentioned Tracy earlier. So you occasionally then hook up Tracy to profile your stuff. I tried yesterday to use instruments in macOS, but it's a sampling profiler. And I tried to run super HTML to auto-format the langgraph, which is a pretty chunky HTML file. And it was too fast. It didn't sample anything. I was looking at the flame graph and there was nothing there. So would you suggest to just use Tracy all the time?
I honestly don't know. I am not familiar enough with profiling things. I haven't used Tracy much, to be clear. I've used it a couple of times when dealing with incremental compilation things. because incremental compilation, when I'm working on the order of like microseconds, which I typically am when I'm testing incremental compilation, I need to know exactly what it is that's taking time, and Tracy can be really good for that with the right integration. So, for instance, I could see that on this incremental update, it's rescanning over this namespace, and it doesn't actually need to do that because nothing in the namespace changed, but it's redoing that, and that's taking 50 microseconds or whatever.
I should look into using Tracy. I think I used it briefly when it was originally discovered and introduced by Andrew in the code base, and then after that I completely forgot everything about it. The only thing I remember is that it has docs in the form of a PDF file.
It does have, yes. And if I remember right, that PDF contains exactly the right level of sass towards Linux distro maintainers who make stupid choices that make Tracy hard to use. I might be wrong, but I seem to recall that. Wow, this is building slower than I thought. I am strongly considering. Oh, hey, Emmy.
Hey, Emmy. By the way, that is so cool seeing incremental working. Holy cow!
Yeah, it's for when you're fixing a lot of compiler errors. Like if I do a big refactor to the compiler, and I have I hit build for the first time in 5 hours, and it spits out 80 compile errors, and I know that every time I fix, I'm gonna make 2 more for the next half hour. Adding incremental to that cycle is an absolute game changer. It's incredible.
I'm curious though, why does f incremental not also imply watch?
Because they're just different things. Because you can use watch without f incremental absolutely fine. And
sure, but what about f incremental without watch?
F incremental without watch currently isn't very useful. I mean, it's useful when I'm testing the compiler, but not useful.
How would that work then? You would have the REPL, you would trigger manually through the REPL?
No, in future, that would be serializing the compiler state to disk.
Oh, okay, I get it.
Like, currently, incremental only works if the compiler stays in memory. But we have a lot of the kind of background machinery in place for serializing and deserializing state to and from disk. Wow, this takes a while.
Will Zig also provide tracing as it kind of does with fuzzing? So I'm not 100% sure how all this stuff works, but with fuzzing, it kind of basically, I believe that the way it works is that Zig puts in function calls to a function that then will be provided at runtime by the fuzzing runner. I guess you could do the same for something that isn't a fuzzer, but is a tracer though. So the tracer runs your application, provides those functions.
I just realized why this is taking so bloody long to build. It's because Jacob's added all of these tests for the back end, and there's I think 50,000 lines of tests he's added that just run for this back end. One sec, I want to see how big these are. Sorry.
So Andrew, I guess the question is, this is an interesting question because now, as I was trying to think through and saying out loud what I remember about these things, it seems that it would be possible to implement something like this if you want. But I don't know if tracing technology, I guess then the other half of the question is how does tracing normally works? So Tracy, you know what? There's also another problem, I think. Tracing is expensive and you generally want to trace only the things that you care about. I'm guessing you don't want to trace every single function call everywhere. While with fuzzing, you do want to do that. Or rather, you're more likely to want to do that, I suspect. So it's an interesting question. I think that the answer needs to come from somebody who has more direct experience with these things. I think you need to ask the other Andrew this.
I'm sure we'll get to the end of this compile soon. Actually, while that runs, what we can do is... Sorry, my launcher keeps opening on the wrong... Okay, there we go. we can take a look at the other bug. It's very possible we fixed it. I don't remember. It may have been another bug
yeah,
in
what was the other one? I also have it on my computer. Let's see. SEMA incorrectly simplifies runtime float vectors multiplied by zeros. Yeah, we did, I think, because it was part of the problem where it wasn't doing element-wise operations, I think.
Yeah, okay. That makes sense. Okay. Okay, so we've fixed both things at once.
By the way, Jacob Lee mentions also that as a bonus, there's like lines in his behavioral tests.
I will do that. Do you know what?
Yeah.
Go on.
No, please.
No, go on.
Oh no, sorry. I don't have anything else. Please.
Oh, I was just wondering whether I should kill this and just build a faster compiler to do it, but no, I'm going to leave this going. I'm too far. I think
you're too deep into it.
We're getting there. It's hard to tell, but my instinct, based on the number of analysis, is that we're nearly there. What are you using if not Tracy, Perf, and some visualizations? As in when I'm benchmarking compiler changes, I tend to just use Poop, like Andrew's, as in Andrew Kelly's. Yeah, that like simple little thing that just compares like wall clock time and a few like statistics, including peak RSS and some lower level things like branch misses, cache references, stuff like that. And I will essentially compare the old compiler to the new one, doing a bunch of common operation or like non-trivial operations. So like building the standard library tests, building the compiler itself, those are the main two interesting cases.
While it's building. Okay, so this is an eBPF profiler, but is this, so I'm guessing this is not sampling then, or is it? It has to be sampling because you otherwise are not, because you're not integrating with it explicitly, right? Yeah, I should probably hook up Tracy to Super HTML.
How many tests has Jacob added? Behavior tests used to, even with a debug compiler, they used to build in about 20 seconds. These are all in math. I don't even know if we've done mem yet. Okay, mem. Oh, mem's nice and compact. Oh my god, it's now just on code generation. That means we're most of the way there. I think we need to wait for this number to hit something quite high.
We just need to invest a little bit more. It just needs a little bit more investment on our part.
We're the vast majority of the way there. It's going to be really funny when all of these build and like half of them fail.
Okay, so in the end we ended up fixing both.
Yeah,
both
a while
bugs.
Fixing 2 bugs. Yeah, and making the code a lot better. Definitely fixing some more bugs.
Yeah, some more that were not reported.
It's actually possible they were reported. There were. Let's take a look, because Jacob reported a whole bunch of issues at once. I picked ones that weren't tied to any existing PR or anything.
To be fair, if Jacob reported these two, he probably caught also all the other ones.
Dividing. So that's one that we just fixed, and one we know we fixed.
Compares floated count.
Okay, actually, none others of these, because the others are comparisons or divisions.
Right. So that would be other operations. Oh my God.
Yeah.
Where there's probably the same
Probably, yeah.
messy code that needs to be moved.
Yep.
Mm-hmm.
Okay. We're at 74,000. I think this may need to get to around 100,000, but
We're getting there.
slowly. I think my theory for what we do after this is we move on to what was going to be the third part of the stream, but since I accidentally merged the second part into the first part, we can do it now, which is Loris comes up with a compiler feature to implement all by himself.
Right, like a new built-in.
And
I don't know.
new built-in.
What does chat want? So if you could have a new built-in in Zig, what would you want to have? Which, by the way, there was a point in time where we were mentioning earlier in comp time. There was a point in time where people really wanted in comp time, and Andrew didn't want to have it in the language. I don't remember how that discussion evolved after a while.
The way it happened was I convinced him.
Oh.
I convinced him on that one. I think it was the right call. I understand why he was somewhat against it, because people do abuse his in comp time.
If I remember, his main argument, at least when it comes to, like, let's say user-facing behavior, was that, or like user behavior, was that in comp time could potentially make people want to create functions that they define as only runnable at comp time on purpose, which he thought was a bad idea, because if your function could also work at runtime, then why are you restricting?
Or that? Even worse, say this can only run at runtime because you reckon it should only run at runtime.
Holy shit, yeah. Or even worse, yeah.
Yeah. And people absolutely do that. And wherever I see it, I tell them, no, don't do that.
How about Rust-like attributes, annotations in Java on structs and fields? Man,
that would be a huge change.
That would be huge. That would be change the tokenizer, change the parser. Now your memory layout for ZR for the AST and then the ZR information for struct fields is different. That is non-trivial work.
Yeah.
Let's think of like a built-in maybe.
Yeah, I think a built-in is definitely the best way to go here, because built-ins are pretty easy to implement. Also, I'll have to show you how to do it in the bits of the pipeline we've not looked extensively at, but it's relatively straightforward in those bits. I kind of need to use the bathroom, so I think this is an opportune time for me to take a quick break while we wait for this test to finish building.
Sounds good.
So I'll return in a couple of minutes.
Okay. Build time. I know Zig has strictly no warnings, but one thing I would really like to be notified somehow about is when I'm using something that is deprecated. Technically, this could be implemented even with status quo. The way you could implement this is basically if you... Okay, so just to be clear, I'm suggesting this as a way of, did you know that you could do this? I'm not necessarily saying that's what you should do. That is what the language design expects you to do. It might be that maybe eventually there will be a let's say language integrated way of doing what you described. But for now, here's how that would work if you were to implement this in userland. Well, the idea is this. Let me pull this down, move it here, and move it here. So the way you would do it is, like, let's say that you have a deprecated function, right? So function old foo. So in function old foo, what you would do is when you want to take it out completely, you can do add compile error, deprecated, use new foo. And that works. The problem is, this is past deprecation, right? This is like you do get the compiler error instead of getting a complete not found. Yeah, there's a bunch of R's. But you can't like optionally be told about this stuff. So one way you can make this somewhat opt-in would be by having branching over it, right? So you would have if options dot I don't know, deprecation. And then when this is true, you have the compile error. Let me set the language Zig. Yeah, so there we go. So how that would work then, options. The idea is that options would be would be a package that you create, that you define in a build script, right? So you have basically in your build.zig. So let's say that this is your main file, and in your build.zig, instead you have this. You have const options. It's going to be b.add options. And then you have ops.add option. This might be slightly pseudocode. Like it works kind of this way. I'm not 100% sure I remember correctly these function names, but the logic is kind of like this. So b.option, and then the option is going to be bool, and then it's going to be deprecations, and then it's going to be if set deprecated decals become compile errors. And let's put it in a function so that we don't get complaints anymore. So you would do something like this.
It looks like they came back just in time.
Hey, Matt. Yeah, so then you do something like this. To be clear, in case it's not immediately obvious, the difference between add options and b.option is that b.option defines a CLI argument that you can pass to your build script. So this basically means that you can do zig build and then -d deprecations. So this creates this, and then I think this has to be like this. Sorry, something along these lines. And then by passing this into add options, this creates a module that you can then import in your file. And so that way you can do stuff like this, and you can do. You mentioned writer, right? So you can do const writer equals if options and deprecations. Oh, you're right, or else false. If option and deprecations, then it's a compile error. Else generic writer. So this is how you could pull it off in userland if you really wanted to. Yeah, I would say that it is fair to say that deprecation, not wordings, right? Because we don't have to have wordings, but like opting into deprecation errors is a common use case enough that it might be worth streamlining this process. At the same time, you know what? It's interesting because it's kind of a spectrum. Like sometimes maybe you could think that there is like a precise line that says, oh, this thing is so common that it should be totally be done, offered an integrated way, versus, oh, this is custom enough that it shouldn't. But there's also a lot of things that are very common, but the language cannot reasonably streamline them for you past a certain level. I'll give you an example, like logging to a file in an application that is long running and where you need to log to a file, but the log file should be placed in the correct directory, right, in the correct position on the file system. So to some degree, you need to. There's some, let's say, infrastructure that you need to build for your software once you reach a certain level of like seriousness that you need to build yourself. Now, whether this should lie, I don't know. I would argue that probably this lies more towards the side of things that are like so common that the language could offer. Yo, maybe we answer this ourselves. Shall we add a deprecated built-in that does this?
Is that the answer? Is that what you're doing?
I think that's the answer. I mean, let's do it.
Go ahead. Yeah.
Let's go. Okay, so let me pull out.
I want to be clear to the chat that this feature is not going to make it into the Zig compiler. We're making a feature for fun.
Yeah, just so that we're clear. Okay, so what's happening in your stuff? Yo, 0 failed.
What's happening here is that we passed the tests. So that means we didn't regress anything, and as far as we can tell, we fixed Jacob's issues. So this is great. Well, I will leave this for now, but after we end the stream later, I will add any tests I need to. I will package this up into a diff, and I will put co-authored by Laura.
That was great. Good job, man. Like, by the way, what in the end, I have to say, you kinda made the F incremental thing slightly underwhelming because you got everything right first try.
Yeah, slightly. I mean, it wasn't first try. I had to like rebuild twice, but yeah.
Yeah, there were a couple arguments that were not the right argument fair. Like it was PT instead of ZCU, but that's like that still counts as first try in my book.
That's fair.
Yeah. Okay. So I'm gonna turn off your screen share.
I'll just turn that off on my side then, so we don't need it.
Okay.
Okay.
So
that put down a little. I don't need it now. Look at the big screen where I've got Christoph in front of me.
Yeah. Okay, so the idea is then we want to basically implement this, but as a built-in. So the idea is instead of writing this, you do const writer equals @deprecated. And then, so this is gonna need us to do some little bit of extra work because then we want to do this. But then that, I think, for us to implement it correctly, will require us to add something like F deprecated. Because we need to be able to turn it on and off. By the way,
here's what your first prototype what it can do is, while Zig doesn't have warnings, what you can do is just make the compiler spit something out to standard error when it sees a deprecated thing. So that can be your first prototype.
Yeah, for sure.
And then after that, we can look at adding the option.
Okay. So for this setup, you know what, though? I need to go to the restroom as well before we start. But I'll... let me write this as, I don't know, idea.zig, I guess. But here's what I have. I have a let's see, uname a. So I have a x64, x86-64 Linux machine that I'm SSH into, because I wanted to use the incremental stuff. I wanted to be able to debug the compiler using Jacob Lee's fork of LLDB, which I have built. This is his fork.
Which we actually haven't demonstrated yet. I just thought, because I didn't end up debugging anything.
So, well, I'm sure there will be opportunities now that I'm in charge. So it's an Intel machine, because our custom backends and incremental. Well, I'm guessing it's more a backend thing, but that only works on x86 Linux, so that's what I needed to have. And I have Linux on my machine, but it's ARM Linux.
Yeah.
Okay. So we're SSH'd into our machine. So let's see. Okay, let me go to the restroom very quickly, and then we can start this part.
I will not put your whole chat against you while you're gone. Is that okay thing? Well, that could probably be The implementation of the deprecated. So no, I think Loris's thinking here isn't that like it would defer to a custom implementation. It's that it would just spit out a compile error if you use that thing. So you don't need any other parameter. Keep Loris away from my computer. But yeah. I mean, wait, I think we're business partners. I don't get to say that he's crazy. Okay, yeah, built-ins, that makes sense. Yeah, I think we're business partners in this brand new like Zig compiler. What's the stream title? I don't remember. Let me check. I'm really clued in on everything that's happening, as you can tell. Compiler Detective Agency, that's what we are. Yeah. So it's probably bad for business for me to attack him. Hi, Loris.
Okay, I'm ready.
We said nothing about you. You weren't discussed.
Okay, so what? Okay, so what do we want to do? I have my source code.
Our recruitment requirements are that your surname is either Lugg or Crow. So the detective agency is a very exclusive club.
Yeah.
Only the best.
And you also need a history of alcoholism and like you need to have lived the detective mood for your entire life. Yeah.
You need to have watched your wife die in a burning building while you couldn't save her.
Something like that. In other words, you need to have experience programming in C or something like that. No. So, okay, I have the compiler. I have Zig, which is it's my release fast compiler. I have Zig1, which is my debug compiler, which I built previously, like this.
Okay, stage 4, no lib. 1 sec. I'm slightly overlapping your terminal. Can you?
Oh crap! Sorry.
It's okay. I just can't quite read your command line.
Oh my god! I was trying to fix this in OBS, and I just realized no. I'm now on my actual machine.
Oh,
there we go. Okay.
Okay, no langref. So you don't need no langref. That's implied by no lib. There's no harm having it, but it's
okay. Oh, I'll get rid of it. That's good.
Use LVM false devx. Yeah. So I should mention, since I didn't use that argument, what that ddev argument is doing is it's saying don't build the full compiler, build a more minimal compiler, which only really supports using the x86 backend on Linux, self-hosted. So, for instance, it won't have the LLVM backend. It won't have Zig build, like the build system. It won't have all kinds of things, but it will work if you just want to use like Zig build XE when building for x86 64 Linux. So the advantage of this is that you get it, like it's just faster to build this compiler because there's less stuff in it.
Okay, let me do one thing while we're at this. Let me simplify my fish prompt. Do I have this? I thought I did have fish prompt personalization because this prompt is ginormous.
It is a pretty big prompt.
Yeah. We do this. Do I just need to create a function called fish prompt? Why am I should not be trying to do this, but it annoys that prompt so long annoys me so freaking much. Yeah, I know that it's my host name being long, but still. Where do you put this stuff? Fish config prompt show. Fish config. Oh, fish config prompt choose. Wait, what? Wait.
Oh, have you figured something out?
Okay. I like informative VCS. I think I'll go with informative VCS, maybe.
Yeah.
There we
Nice.
go. Okay.
That's better.
Sorry for the technical difficulties. Okay.
At least your screen isn't just randomly turning off.
Okay, what were we doing? So we were saying we want to add this new feature. Yes. Okay, how do we do this?
Yeah. Okay. So the first thing, so we kind of want to step through the pipeline. So obviously at the start we have parsing. Actually, we're not going to need to change parsing because you're just adding a built-in. And like built-ins use a standard bit of syntax. It's not like the parser is handling each built-in specially.
Yeah, it's at identifier.
Yeah, exactly. So we're actually going to want to start in ashgen. So we're in lib / that file.
Mm-hmm.
Okay. So this, as with actually, frankly, most phases of the compiler, this is another big switch. But yeah, okay, yeah, so you've jumped ahead. We're going to end up in built-in call. So this function here handles every single built-in.
Oh, this is the function. Oh, yeah, you're right. Wait, go to... Can I go to function start? Let me see. I think it's this. Go to previous function. No, go to previous. I'm not pressing the right button. Function. Oh, that's me, Max. Okay, go to next function. That's built-in call, but it gets me to the end. God damn it! I guess I can do curly curly.
Come on, there you go. Wait,
I don't know. Sorry, I'm not sure. In any case, so in comp time we were saying. So in here we're handling all these guys. Yeah.
Yeah. If you quickly scroll up to the top of this function, as long as it's going to take you to get there, since apparently your editor doesn't work. Nearly there. So if you go up a few more lines, just pass the switch to the actual top of fun built-in call.
Okay.
So you can see, so down a few, you scroll past something important. Okay, yeah, that's the line I'm interested in there.
Yeah.
So you can see that it's actually, we have the built-in name, which is just a string here, and we're actually getting it from a big list of these built-in functions. So yeah, there you go. This built-in fun file has all of the built-ins listed in it. So we're going to want to add one.
Yeah. A, B. Oh, they're not sorted alphabetically. Oh no.
They're like somewhat kind of alphabetical-ish. It doesn't matter since, you know, we're not going to be PRing this. You can throw it wherever you want.
Okay, I'll put it at the very end.
Sure. Mm-hmm.
Illegal outside function. No, it's illegal inside function.
Outside function. It's is it illegal in a function? Why would it be illegal in a function? I think it's fine anywhere.
You think so?
I think so. If it's analyzed, it emits the warning or error or whatever. So you can actually just delete that line since that defaults to false.
Yeah. So evolve to error. Info about the built-in calls possibility of returning an error. So I think in our case, our can return an error.
Yes, it can return an error. Yes,
right.
Because
so
if you pass an error in, then
allows that value false. So that's good. Okay, so we want to change this to eval.
Eval to error equals dot maybe, I believe, because yeah. So the reason we want that it wants to know this is because ashgen is going to use this information to figure out what instructions it needs to emit regarding things like the error return trace. ashgen wants to know whether an expression might be an error so that it knows whether it needs to pop the error return trace in certain cases. Now you've written there .tag equals .deprecated, which is correct, but obviously you've not added that tag anywhere yet. So I think that's going to need to be added somewhere. Yeah, so you'll just need to throw it into that enum.
Can I not go to matching bracket? It doesn't work. Yeah, this is the... actually, I think this is not ZLS. This is the Trisita grammar that has poopy queries, I think.
I see.
Okay.
Okay, cool. Okay, so that's the built-in fun change done. So now we can head back to AshGen, where we were earlier.
Okay.
I just noticed that the file you got bitten in the arse by ZLS there. Look at the file path you're in here.
Fuck. Yeah, I did.
See, this is why we do this stuff ourselves and don't rely on the foolish tool.
No, I could take out but it is kind of correct. It's my fault because I have a copy of the standard library in the Bootstrap compiler directory.
Oh, of course, that probably comes from import standard.
Yeah. Okay, so let me do this.
Okay, just make sure to apply that same change to.
Wait, no, I think I can. Can I not just nuke build? The lib under build.
Wait, delete under where? As in, do you mean delete lib there?
Yeah, and start using the main one.
Yes, but before you do that, could I suggest copying the lines you just wrote into the file? I mean, I guess you can just write them again.
Yeah, I was thinking of just redoing it.
Okay, yeah, that's fine. You can just delete lib there. That should work fine. Okay, let's try this again. So AshGen, and you want built-in fun.
Yeah.
Okay, that's the right one. Okay, so yeah, so you want to add your tag there, and then you've got the big old list.
Okay, let me try here. Okay, this time it worked. Can I?
It's just a val2 error.
Oh. Wait, is it can or just eval2 error?
Just eval2 error, because then it's
okay.
.maybe. Yeah.
Okay. So,
cool. So
we're
now
back in business.
Yeah. So, yeah, sure. So yeah, this is a big switch over all the built-ins. You can throw it wherever you want in here. It makes no difference. Sure. .deprecated. So the question is, what do we want to do here? I'd suggest opening a block.
Yeah, we implemented inline. Okay.
Yeah. So okay, what do we want to happen here? There's a single argument to this built-in.
Yeah. We want to print something and return it. Right. That's our
yeah, exactly.
Our POC.
So what I might actually suggest is initially we just don't even print anything. We just make it like a no-op built-in, and then we can come back and add the printing in a second.
Okay, that sounds good. So how do we return our argument?
Okay, so there's a function you're going to call. It's called expr, expr. Yep. So expr is, you know how in SEMA we had like analyze body inner, which was kind of the main loop of SEMA.
Yeah.
Expr is essentially the main loop of AshGen. It is a big switch statement over all the AST nodes. So what GZ and scope you're already going to have. GZ is basically telling it to AshGen where to put ZIR instructions. Scope is the scope, so it can it's like tells it what variables are in scope, things like that.
Yeah.
The next parameter RI is about result locations and result types. So yeah, again, pass it through unmodified, because like, you know, the result location of the built-in call, we just want to forward onto its parameter.
Yeah.
Because this built-in is essentially a no-op. The only thing we want to change is node, because this is the actual thing. So we want to go exactly param 0. So for now, that should work completely fine as your AshGen change, and we'll come in later and make it actually print the message somehow.
Yeah. Okay. So I guess what do you want me to do? Should I try to rebuild the compiler and try if it works or what?
Yeah, I mean, it's not going to work because we'll get some errors, but like try and build it anyway, and we'll see what we get. Because this is a nice way of like compile error driven development. Is like, did you just close your session? Oh, okay.
No, I opened another one. Oh shit! The prompt stuff is not. Oh well. Okay. So they build this one. Do I want to do also incremental? I do want to do incremental, right?
Yeah, you can do F incremental watch. That works. Because actually, yeah, that makes perfect sense. We're going to spend a couple minutes fixing errors and stuff. So, actually, Control C that, because you should also pass deno bin, because otherwise you might crash the compiler. You probably won't, but you might.
Okay.
So what I'm expecting to see is there are going to be a few switches that are complaining about not having, like, not being exhaustive, like they're missing that new built-in.
Maybe I'll put it here.
Actually, wait, am I? I don't even know if I am expecting that. I think this might.
Wait, you know what? I was thinking I could make it small because I want to show it on screen. You know what? I'll
rerun it with prominent compile errors then.
Yeah.
Yeah.
I was thinking also of maybe font size down a little bit, and then let's see if we can squeeze it somewhere between us.
Yeah, that works.
Something like this.
Okay. So yes, you're missing one thing, which makes sense. So you can see the file it's complaining about.
AST RL annotate. Yeah, so there's other places where now we introduce something new, we need to worry about it. Okay.
Yep. Okay. So I can explain this file. I mean, to be fair, the comment at the top pretty much explains it, because I wrote this whole file, so I actually tried to document what it does.
Let's see. AST-RL annotate is a simple pass which runs over the AST before AST-gen to determine which expressions require result locations. In some cases, AST-gen can choose whether to provide a result pointer or to just use standard break instructions from a block. The latter choice can result in more efficient AR and runtime code, but does not allow for RLS to occur. Thus, we want to provide a real result pointer from analog only when necessary. To achieve this, we need to determine which expressions require a result pointer. This pass is responsible for analyzing all syntax forms which may provide a result location, and if sub-expressions consume this result pointer non-trivially, e.g., writing through field pointers and marking the node as requiring a result location.
Okay. A lot of words there, which I'm not sure how many of them you've understood, because possibly requires knowing a bit about ZIR that you might not. But the point is, yeah, it's happening before AST-gen, and it's, again, just traversing the whole tree.
Yeah.
And it's just annotating a very small amount of information on it. So I'm guessing that I have a function called built-in fun again, or something like that. Yeah, search for... well, yeah, actually, you can just look at where I'm using built-in fun.
Okay, check this out. Go to references. Use it here.
Okay, there you go. So I am traversing all the things. So you don't really need to understand what this pass is doing. I can just tell you what to do.
Return false? I mean, in our case, I don't know. In our case, we don't do anything like this, right?
So you don't, but the thing is, because we're just passing because we are literally just acting as if we're the same as the child expression, we just need to forward this query on, essentially, unmodified.
Understood. I see. Okay, so we want to, do you call yourself? Do you recurse? What do you do?
Yeah, you could recurse it.
You recurse through expression? No. Wait, do you recurse directly or do you recurse through expressions? Because I see that you call expression a lot. You never call yourself directly.
Yeah. You recurse through expr because you don't know that the thing within you is going to be a built-in, do you? Like, so you recurse by doing, just return RL or ast RL to expr. Oh, you're a return try person. Interesting.
I don't know. I actually don't have a strong opinion. I was just monkey copying. I was just like AI style replicating what I saw elsewhere. Okay, so args 0, I guess. Block. Result info none. Result info type only.
So can you scroll up to the top of this function?
Yeah.
I'm pretty sure you can just forward the RI that you've been passed in this case. Because essentially this you want a comma, not a semicolon at the end of the. Yeah, there you go.
Okay.
Because essentially this built-in is acting as if it's not there, right? You are literally just trying to forward the query straight onto the child. and return that exact same
Currently,
information.
no built-in confirms its result location.
Yes. So there's a discard there that you should comment out. There you go. Okay, so you fix the compile error.
And now
So
we
now,
built.
well, sorry?
Now we built successfully.
Well, it's not actually going to have built because you passed deno bin, remember?
Right.
So, but if you rerun the command without that,
yeah.
bin,
So we don't have compile errors anymore. So I can do without deno bin.
Yeah. Oh, you probably delete effing. It's fine. You'll have to Control C this after it finishes, but that's fine.
Oh, because it stays open. You're right.
Yeah, because you've left watch on, and you've told it to do incremental, which is a dangerous.
Okay, you know what? Let's just do it normal. Okay.
Okay. So what you need to do now really is write a little test file that uses your new built-in.
Yeah, test.zig. So let's see. I don't know. Let's print a number and then we deprecate the number, I guess.
Sure. Brilliant. So obviously your local hash check's going to be complaining because that doesn't exist on master, but that's fine.
Yeah.
So
yep, actually, sure. Run.
So what are we expecting to happen here?
Just running correctly, not saying anything, just work.
Yeah, exactly. We're expecting it'll just print 10 because we've not told it to do any actual deprecation thing yet.
Yeah.
Oh, it'll take a minute on this compiler RT file. Funny story. This is because that file has a bunch of really big integers in it, which the parsing code for big ints uses an allocator, and it's very irresponsible with how it uses that allocator. So when we pass it the really slow debug allocator, it takes ages. But okay, it seems like we're in CodeGen now, and it sure is taking its sweet old time. This is the downside of... Okay, there you go. 10. Perfect. So that's what we expected. That's working.
Yep. Okay. Now we want to start complaining.
Yes. So you're going to want to go back to AshGen, AstRL and annotate. You're not going to need to touch again. So what are we going to want to do here? Well, this is ZIR, so...
Yeah. I guess here's what I would say. I think for me, the next step would be, let's have an if where the Boolean inside we hardcode for now. And depending on the value of that Boolean, on one case, we return the sub-expression. In the other case, we want to return this into a compile error.
Okay, so I can see why you'd think this. That would make sense when you look at the pipeline in isolation.
Yeah.
However, it's not quite right. The reason is that ZIR is cached globally. So ZIR is not allowed to depend on any compiler options or anything like that.
Understood. So that means that we need to issue an instruction that makes SEMA do that.
Exactly. So we need to issue an instruction which says, if this flag was passed, then you should be emitting an error now.
Yeah. So we basically want literally a deprecated instruction.
Yeah, absolutely.
Okay.
So I would suggest you're going to want to add that instruction before we modify AshGen.
Sounds good. Where do we go?
zir.zig.
Right.
Yep. So this is where zir is stored, and there's all kinds of stuff here, but we're interested in the instructions here. So these are the main instruction tags.
Yeah.
This one, actually, I would probably add as an extended tag. because you're not going to need to associate any data with the instruction other than a source location.
Yeah.
So it would just be quite silly to use up one of the normal tags, because like space in that item is at a premium. Whereas in the extended tag, we have 65,000 available. You're going to be fine. Yeah, just search for extended. And then you can throw it at the top or bottom of this. It really makes no difference.
This stupid query doesn't know how to go to matching bracket inside of like an enum definition. That is crazy to me. So okay, you know what? Sorry, small aside. This why it's like a bit of trivia that might interest you. So we used to have a three-seater grammar that was maintained by somebody whose name I'm forgetting, but the person was like a member of the community for a very long time, and they've done the maintainership work for a while. Then I think life happened, and so they started. I guess they got tired of updating the freaking grammar every 2 weeks. So now there's another project that it's kind of trying to make to streamline a bunch of three-seater grammar development processes. Like they basically have one repo or one organization, on GitHub where they collect a ton of grammars. And so they have a more up-to-date version of the Z grammar, which I believe now Helix has started depending on. But now that brings a bunch of quirks of its own. And so that's why go to matching bracket is not working.
Yeah. Okay. Yeah. So at the end here, you can throw in deprecated. Now you'll see that in the doc comments for each of these instructions.
I need an explanation for this. I guess in our case, it's we want to be a UN node.
Okay, so actually that system is not what we're using here, because we're using the extended tag.
Oh yeah, right. UN node is for the top level ones, right?
Exactly.
Right.
So
here
what
we just have data
is it's actually on your screen right now, inst data at the bottom there. So opcode is the thing you've just filled in, and then you have small and operand, and you just choose how to interpret them. We haven't bothered using a union here.
Yeah.
Now you actually don't have any data you need to pass here. This is basically just an operation which maybe fails depending on some flag you pass the compiler.
Mm-hmm.
So the only thing we need is a source location, right?
Okay, yeah.
And so what you're going to want to use there is source locations are stored as 32-bit signed integers. They're signed for reasons that need not concern us to do with incremental compilation. So if you scroll up a few lines and look at, okay, in place arith, no, that doesn't. There must be one. Wait, freeze here. Damn it, you scrolled very bottom of your screen right now.
Okay.
Last line, operand is source node I32. That's the kind of thing you want. So that's kind of how we write this, is we say like operand is this value with this type. And that's exactly what you're going to want to do here. So operand is our 32-bit value we have available. And we say, okay, we're going to use that to represent the source location.
Yeah.
And it's going to be a AST node index. The reason it's signed is because it's actually an offset from a different index. The idea being that on incremental updates, other bits
I remember that
might change.
Yeah, I remember that all the offsets are relative, so that you need to fix up fewer things whenever you recompute incremental stuff.
Exactly. Yeah.
Mm-hmm.
So yeah. Okay. So now we have an instruction. Now we need to make ashgen spit out this instruction.
Yes.
Okay.
Yeah.
So, do you remember? This is a little memory test.
No.
Which argument I told you stores like the ZR instructions that we're building up? The variable you've got here.
The one that stores the instruction they were outputting, I think, is GZ, right?
Yes, correct. So GZ stands for Gen 0.
Yeah, I remember when this instruction was introduced. I remember I think the point was to do some batching work, I believe, right? When no, you know what? It's been too long. I don't remember all the details, but I remember when it was introduced.
You might be thinking of the GZ stacking system, which is a clusterfuck, but luckily we're not going to be interacting with it.
Okay.
Okay. So GZ has a bunch of functions on it for adding instructions. If you have auto completion stuff, you can probably. Oh yeah, sure, that works. They're not pub, right? Because they're just used within this file.
Oh, right, we're in the same file. Yeah, so unstack is empty. Instruction slice up to...
We're not worried about any of these so far. Still not worried. There's a lot of stuff before we get to the interesting things, it seems.
Oh, I see. If you tell me what I should be looking for, I'll do
we're
that.
nearly there. This is a big function, but if we're past this one...
Wait,
okay, here we go. We're getting to interesting ones. So all of these functions that start with add, adding instructions. So what I'm going to suggest looking for is functions that start with the name, that start with add extended.
Yeah, I assumed.
Extended payload, extended multi-op, extended node small is probably the best one. Yeah. So this lets you pass in a source node to go in operand and anything to go in the small value. Now we're not using small, but we can just pass undefined there.
So gz dot add. Was it? I already forgot. Function add x.
You're in there, aren't you?
Oh yeah, right. I need to be in. Is it still in the AST-gen, right? Okay.
Yeah.
Man, this SH connection thing, like being slow, it's killing me. Extended small, we were saying, right?
It's like add extended node small, I think, because it's saying that one thing is an AST node, and you have there you go. Okay,
opcode is gonna be dot deprecated.
Yep.
Source node is gonna be.
You have it here. It's just called node.
But we're passing the node to the full built-in then. I guess that's fine.
Okay. Which I think makes sense.
Okay, small, whatever, 0.
Yeah. So like technically speaking, it could be undefined, but we actually tend to avoid making it explicitly undefined because that means we write undefined bytes to disk when we cache CIR, which then makes validation tools angry.
Understandably.
Like it makes Valgrind angry. A couple extra things. That function returns an error because it might so you'll just need to try it. And also, it actually returns a zref. The idea being that often we're going to want to reference this instruction and like use whatever value it returns. In this case, if this instruction, if we get past it, it's not returning any value, right? We're not doing anything with it.
Yeah.
So we can actually just discard this. We don't care about the ref here.
Okay, but wait, don't we need to return something? Wait a second. I'm a little bit confused now.
Okay.
You call built-in call, and then returns. This returns a. What does it return? It returns a.
It returns a ref. So it's returning whatever the result of this built-in is.
Right. So why are we not returning this?
Because there are two things we want this built-in to do. The first is it should emit this deprecated instruction.
Yes.
Which will maybe compile error. But if it doesn't compile error, then we just want to evaluate whatever's in the parentheses and return that, right?
Correct.
So the deprecated instruction never has a result that we care about. Like it will only return the result void or
understood. Okay, I get it. Okay, I get it now. Yeah, so this generates a deprecated instruction, and then otherwise everything will continue referencing its child.
Exactly.
That's perfect. Okay, I get it now. Okay, so this should stay like this. We're done.
Yeah, we're done with AST-gen now.
Okay.
So now if you, you don't start a incremental build, watch again, no bin one. Yeah, I was going to say, there you go. So I'm expecting to see 2 compile errors, I think, but I might be wrong. No, I'm expecting to see more than 2. I'm expecting to see 5. Let's see how right I was. 4. I was close enough. Okay. SEMA is the interesting one. We'll deal with that later.
Okay. We'll see how the CLS does then. Okay, next.
So print zir we can also deal with in a second. Let's not worry about it. Oh yeah, those are just notes. So the first two there, let's not worry about. We can deal with those in a minute.
Oh, print ZIR. Understandably.
Yeah, sure, let's do that. So yeah, it's saying there's a missing tag in the switch on line 526. So if you look at what this function's doing at the top, it's printing the built-in name and the parenthesis, and then it's expecting you to finish it off, and you'll do the closing parenthesis and stuff. Write X node might actually be what you need. I think that might do exactly the right thing. You should double check what that function does, but I'm pretty sure it's just going to assume. Yeah, so it does the closing parenthesis, and then it writes a source node. It like interprets the operand as a source node, and it ignores small. It doesn't do anything with it.
Yep.
So that's perfect. That's what we want. So now at the bottom of this, I expect you have some errors. Yep.
You're now down to 2.
And ZIR. So let's do the one in ZIR because that one is fairly easy. That is a big switch, something to do with incremental compilation, which basically the vast majority of these, you see that comment there that says, once again, we start with the boring tags. This is one of the boring tags. Basically, everything is a boring tag as far as this function is concerned. So yeah, just throw it in that. This is to do with tracking instructions between incremental updates. Okay, so now we've got the interesting one.
It's SEMA time.
It is.
Okay, so 1, 3, 4, 3. Out of curiosity, how do we stress ZLS on this? Well, so far so good. Everything that I'm doing works. It's not pooping itself.
Navigating the file tends to work okay. In my experience, once you edit it, it will explode.
Okay, let's see that happening. So in here we have a switch that doesn't. Okay, we are not analyzing. We don't know how to analyze our new thing. So I guess I can put it up here. Since we're not committing this, we can maybe.
Yeah, you can do
it in
line,
right?
You want make it a bit of a mess if you need.
Okay.
Sure. Okay, yeah. So, so this is where you're going to have that if statement, right?
Yeah.
So you can just do if true for now if you want. And then else. So the else case is actually really easy. In the else case, we just want to do nothing. And the result of the instruction.
Right, complete nothing, because we are analyzing an instruction that just stops things. Otherwise, we do nothing. Yeah.
Well, it's so you can't quite literally put nothing there, because you can see that like this switch, we're doing break ext with the result. So
yeah.
So what we need is to break with the result of this instruction. This instruction doesn't have a meaningful result, right? Like we don't really give a shit what it returns because we're never going to use the result.
Yeah.
So the obvious thing to use in that case is just the void value. So what you can do is you don't want to return because we're in.
Sorry, you want to break.
You can break :ext dot void underscore value. So that's can you guess what type dot void value has there?
Void. Oh no, sorry. No, you're not asking me.
I mean within the compiler.
Yeah, within the compiler. Okay, give me a sec. I guess that's an air instruction.
Yeah, it's an aref.
Ref.
Because
you're right. A ref. Yeah.
Yeah, because the result of the instruction of this ZIR instruction might be a runtime known result from an air instruction, or it might be a comp time value.
Yeah.
Okay. So now we have this if true case. So what do we want to do in here? We want to error, I think, don't we?
Yeah, we want to return a compile error.
Okay. There's this lovely function, SEMA.fail.
SEMA.fail. I think we will need to try it, right?
Yeah, or return, because it always errors. It doesn't matter. Okay. So.
Oh, yeah, because it returns a compiler. Oh, yeah.
Yeah, exactly.
Yeah. Okay. Return fail. So I'm guessing block we have laying around. Source we want to point at So
source we're going to need to figure out, but we can do that
yeah.
in a second. Just write source for the second. We'll make a variable in a moment.
Yeah. Found deprecated what? Value? Decal?
Deprecated code. I don't know. It doesn't really matter.
Okay.
And then obviously format args, you can just do that. Okay, so we need a source location. So you can see a few lines up that we have const extended. So we've got an output extended. We want to get the extended dot operand, I think it's called, right? Because
I was hoping.
I think extended dot operand is the 32-bit value.
Yeah, and then I have to int cast it, right?
Bit cast to a 32, but yeah.
Yeah, bit.
Now we have a node offset. This isn't quite actually a source location yet. I'd call this variable src underscore node. And then to actually, what we want to do is we want to turn that into this thing called a lazy source lock. The way you do that when you have a node offset. Okay, wait, you seem confused.
Okay,
need a moment?
Yeah. Okay. A lock, you said?
Sorry, just LOC as in location.
Lock is in location. Okay, yeah.
Yeah, my bad.
So we have, this is an index in, okay, yeah, please continue.
Yeah, so what we have at the minute is approximately an index to an AST node.
Yeah.
But there are different kinds of source location. You might want to directly reference that, or you might want to say this is a built-in go to its first argument or go to its nth argument.
Mm-hmm.
Or you might want to say this is a struct initialization. Please point to the fifth thing in it.
Mm-hmm.
There's all kinds of types of source location. So the point of lazy source lock, what lazy means is that we've not actually done any interesting work to compute this. We've just kind of thrown, look, here's a node index, and maybe here's like what we want to go to within that as like a tag union big thing. The reason being that computing source nodes, we want to be really cheap because this happens all the time. Mm-hmm. Actually, erroring is the thing which can then be expensive and do the work to figure out where that source location points to. But when we just have a source node like this, it's really simple to construct the lazy source location. What we do is we do block.node offset, and that's a function. And we just pass in source node. Yep, exactly. So all this is doing is block contains the basically, you know how source node is an offset. So yeah, there's so remembering how the I32 there is an offset, block contains the thing we're offsetting against.
Mm-hmm.
Oh yeah, so there's also some funky tracing stuff here, so that we have like in debug build we keep like stack traces for where source locations came from, which I have never used in my life, but you know.
Mm-hmm. Okay.
But then block.source is the kind of interesting one, is that you can see it's constructing it using this piece of state from the block as well.
Mm-hmm. Okay.
So now I expect this will work at this point. In fact, you can see at the bottom of your screen. It built with success.
We built right away. Okay, so we want to do a build, just a normal build.
That looks good. So what I expect to see now is that it will always spit out this error.
Yeah. Yeah, it makes sense that this is in SEMA and not in ASTGen, also because hitting one of these things is not...
I can tell you what happened here. This isn't as scary as it seems.
Okay, but yeah, so as I was saying, the problem is not hitting one, like having one present in the source code. The problem is also hitting it, like you could exclude that at compile time, and then that should not trigger an error. Okay, sorry. So what is the problem here?
Okay, so what's going on here is remember how I said earlier that ZIR is cached globally?
Oh, I see.
Yeah.
We're hidden cache. Okay.
So this
Yeah,
is
I
the
remember.
one case where it's correct to delete your cache.
Yeah.
Never do it otherwise. Report a compiler bug, please.
Yeah, that makes sense.
Yeah. If this now doesn't error, then I'll be really okay. I'm now really confused. Okay, that's interesting. Well, do you know what this gives us the perfect chance to do?
Debug.
Yeah. So actually, the first thing we should do is we should run check t on that file to check that it's spitting out the ZIR we're expecting. So yeah, we'll want to scroll up a little bit. Extended deprecated. Okay, so you can see instruction 5 there. That's what we expect to see. That's working like we expect. Okay.
It is not, well, I think we're not printing it nice though, because it should say deprecated of percentage 4, right?
No,
what am I
because the
missing?
deprecated instruction doesn't contain any like operand to it. The deprecated instruction is just when we analyze it is when we are remitting the error.
Okay.
So it's basically just if you get to this instruction, spit out the error.
That makes sense. Okay.
I'm actually very confused about why this is working, by the way. Your repro is definitely correct, right? Like you're using number in the file.
I am.
Yeah. How on earth is that not working? Okay, well, let's try it. I mean, silly question. You've saved that source/SEMA, right?
Yes.
Okay.
Yeah, you did see compile errors go from being there to success in the incremental thing.
Okay. Okay, well, let's use LDB then.
Yeah. Okay, so I'm gonna make a new window.
Oh god, okay.
Yeah, that's the life. Okay, what do we do?
Okay, so we're going to want to use LDB, the path to your Zig compiler. I don't know if that should work actually. Yeah,
You know also what I'm thinking. Here's what I'm thinking. I think it's a bad idea to give this file in here. Let me move it outside. Okay, just to make sure that everything is happening. So okay, and then
wait. When you deleted the cache? Did you delete both caches?
I did not delete the global cache. No.
There is a chance that for weird reasons this may have gone in the global cache. Could I suggest deleting both just in case?
Yeah. Where is the global cache?
/.cache/zig.
Repeat the first part. I didn't hear that.
Home
home.
like your home directory /.cache/zig.
So okay.
Okay. Yeah, try it now. Oh. One sec. You've disappeared on the thing.
I'm still alive.
Can
you hear me? Oh.
My internet's working.
I can hear you. Hello? Okay, let me try.
Oh, that's really strange. I can't hear you or see you.
Can you hear me now? Test. Test.
I can see I've opened the Twitch stream like silently, so I can see you talking on it. Are you using? I am using Firefox. Does Firefox break your thing? I don't know, but it always disappoints. Let me. If I refresh this, will anything break? Okay, I'll
no,
refresh
really
it.
go for it. Yeah, by the way, it was a cache thing. Yo, Matt, can you hear me?
I can hear you. Yes. Can you hear me?
You need to change your microphone again, I think. Double check that.
My microphone should be fine.
Okay, interesting. You now have a different volume. That's curious.
Okay, I can solve that. Is it? Okay. Do I need to be louder or quieter?
I think this is fine now.
Okay, sure.
Okay, can you see my screen share?
Yes, I can. It works.
I think there is a bug implementation of WebRTC in Firefox that occasionally, in the past, it used to leak memory and have issues, and now it got better, but it might still be not perfect. In any case, yes, deleting the cache was the thing.
Yeah, okay. That makes sense. I'm glad we figured that out because, frankly, going through LDB, that would have confused us more.
Yeah.
Okay, so all we need to do now, I think, is add a flag, right, to turn this on and off. Okay. Okay, that's interesting, then. So we're going to go into main.zig here and look at the command line parsing. So we can, take a look at f incremental. Enable deprecation warnings, I suppose.
I guess in this case, errors.
Oh, well, yeah. Yeah.
Which, by the way, it's not a bad idea if you think about it, because the problem of the warning is that it's stuff that you kind of it's like a let's call it a mild error that you're getting, and you can choose to ignore for as long as you want, and then at some point you decide to actively fix all of them, right? So the idea is, instead of having warnings that keep bugging you, you turn on them as errors, and now it is an error to depend on deprecated code. You do so willingly, and now you basically fix those errors one after another until you're done. It seems not a bad idea. I think it's like decent design overall in the end. Okay, so
yeah, for sure. You should probably add a f no deprecated for consistency as well, just below there.
Okay.
Yeah. So then take a look for f incremental, I suppose, and you can see where that's handled.
Sorry, I was spacing out. You were saying?
Take a look for grep for f incremental in the rest of the file, and you can see where it's handled.
Yep.
Cool. So ignore the dev.check thing. That's something else. But yeah. Okay, that makes sense. So now you want to look for opt incremental, and yep, make another. And now I guess see where opt incremental is used, because I think it's going to be a very similar pattern. Yeah, so this. And here you get to pick the default.
That is indeed a good question. I guess what should the default be? No, the default I think should be false.
Sure. And now you can look at where incremental is used.
So what are you saying with it is not? Isn't it nice to do ZLS? Come on.
No, because I would just have that type /incremental and found it just as fast. Yeah, so this seems like about the right area.
Yeah. So we were talking about this stuff. My SSH session or something just died. I can't move my cursor anymore. So
That's gone well. Okay.
oh shit, we're back. I don't know
You
what
figured it out. Okay.
Okay, so wait, we were saying here.
Yeah.
So we do dot.
So the things you're passing here are options to compilation.create. So
Yeah.
I guess at this point, yeah, you'll want to jump here, add an option. That shouldn't have a default value, by the way. That's really bad form on our part. I mean, I guess it could, but like, there's no reason for it to.
Then I need also to do create.
What, sorry?
Create.
Oh, right. Yeah, you need to go here and actually handle it. Yeah.
Yeah, create options, but then these options don't get passed in one-to-one, right? They get remapped or something.
So they get handled individually. So if you look in here for incremental, just search for the string incremental there, you should find. So yeah, you can see there, that one we actually are passing straight through, and you'll probably want to do the same thing here. And so that's a field on compilation, which is the file we're in.
Okay. Yep.
So you'll want to add that field to the top level of this file.
Sorry, you were saying?
So you'll want to add a deprecated field to this file now. You added it to the options, and you just added a line which puts it into comp.
Yeah.
And comp is a compilation, which is this file.
Oh, you mean the comp struct needs this? Yeah, exactly. You're right, because I added it earlier to the options, not to this. Yeah.
Exactly. Yeah. So you add a deprecated bool here, and this is the one that you're actually going to be able to look at from SEMA.
Okay.
So what you can do here is there might be a comp in scope, 20% chance. Okay, there isn't. In that case, zq.comp. There you go.
Okay, now here's the question. This has implications with the caching system.
Mm-hmm.
So is it done automatically, or do we need to do anything?
What would the implication be for caching here?
Well, depending on whether the CLI argument has been specified or not, those are two different invocations, and so that should cause a cache miss.
I see what you mean. Yes, when you're using the whole cache mode, you're right. I actually don't know this answer off the top of my head. Give me 20 seconds.
Like, I know that some options that you pass in the CLI are not should not influence caching. Some others should.
Yeah. I genuinely need to double check how this works. Oh,
there we go. Look at this. Options cache mode incremental, and then some options get added to the hash, some do not. Mm-hmm. Whole cache also has some of that. Okay, I think maybe we can wing it. Let's see.
Yeah, let's maybe add things to be safe.
Yeah, let's see. Options are specific to Z source files that cannot be modified between incremental updates.
So yeah, you'll want to add it here. I think this is one play. Are you good? Well, you've disappeared for me.
Yeah, I'm good. Okay.
Hello?
Oh God, are we really still having trouble?
I'm guessing that you can still see and hear me, and I can't see and hear you. Oh wait, your screen. Oh, we're back.
Let's go.
Okay, so yeah, that's the incremental cache mode, but you also need to handle the whole cache mode, which is
so whole cache mode. Let's see, arena create. We don't know whether I put outputs and link here until blah blah blah. Subpath cache use. Where's hashing though? I don't see any hashing happening in here. Okay, wait. Let me read more precisely. Hold the star. This is kept here so that link file open can be called later. This is so that when doing cache mode hold, the mechanism in update can use it for communicating the result directory via meet. Okay. Cache use whole.
Okay, well, back where in the code you edited a little bit above the incremental case.
Yeah.
Back up to there. So see how there's that comment saying synchronize with other matching comments just below that one.
Oh.
So if you search that in this file, I think you will find something. Yeah, there you go.
Yeah, there
Add
you go.
non-incremental stuff to cache manifest. There you go. That should be it. Yeah, good spot. I honestly didn't think of the cache implications here.
I remember doing some of this stuff with Andrew ages ago.
Okay, so build a compiler. Actually, do you know what you should do? Cancel that and add an option to the end of this command, -d force -link -libc. Because this means you're going to be using the C allocator, which is going to be so much faster. I mean, it'll still be a very slow compiler. Yeah. It'll probably be like twice the speed.
By the way, for the people watching, of course there's a YouTube channel, and you should subscribe to the YouTube channel. What are you talking about? Like, subscribe, share, comment, join the squad, buy the merch, all that jazz. Yeah. Okay. Wait, let's remove cache.
You shouldn't need to here, but you might, maybe. But yeah.
Yeah, but it's better safe than sorry when recompiling the compiler.
Yeah, for sure. So since the default is false, we're expecting this to work, I believe.
Yeah. I'm going to also run it twice to just to double check that the cache also works as we expect.
We actually don't expect this binary to be cached. So.
Oh, really?
Zig run doesn't do that.
Oh, okay. I didn't know. Okay, so that's fair. F deprecated.
Now, in theory, what we'll see here, if we're very lucky, there you go.
We got it.
Loris's new built-in.
That's not bad. Honestly,
this is Zig 0.14.0-dev.
Honestly, this is not a bad deprecate. This is not a bad language feature. Like, I know that we're not doing this for real, but I think this is worth a pitch. Just saying. Just saying.
If you're on the core team, you're allowed to write proposals.
That's not bad, right? So let's make a slightly more realistic version of this. So the way it would work is something like this. Let me think. So about writer versus generic writer, how would that work? Let's see. So we would have function print, greet, and greet takes in a writer. That's what we say, right? So we say
type any
yeah,
type.
just writer. Since we need to be able to inject deprecated, we're gonna do it like this. Was it iota writer?
I'm trying to understand how you're planning to take an argument of type writer. It's a generic thing. You need any
right,
type.
Writer is generic. Oh, you're right. You're right. So, oh my God, right. We need a better example. Writer sucks. What is a better example?
Writer is too much of a pain in the ass, I think.
We need a better example. What's a good example?
I'm pretty sure. One moment. Wait. No, that's not going to work.
Okay, I know how to do it. Fuck it. Here's how we do it. Check this out. I was about to say we could put deprecated in the standard library. But then if we put deprecated in the standard library, it would require me still to use writer the function. So yeah, no, it's a shitty example. We need something else.
Here's a really simple example. Standard.time.sleep has been deprecated and replaced with standard.sleep.
Oh, really? I didn't know.
Yeah, Andrew did it at some point months ago. Okay. So you can go into the standard library, standard.time, and you can change that.
Okay, so we do std.time.sleep.
You can do like standard.time.nanoseconds per second. I mean,
yeah, SEO-time.ns.
because 2000 was not going to sleep very long. I was going to sleep for 2 microseconds.
So this is it, and then we can go in the standard library and actually deprecate it.
Oh no, because it's jumped through the alias. It seems it's gone to standard.thread.sleep. If you look at the file you're in.
Yeah, you're right.
Too smart.
Oh, there we go.
So there you go.
Okay, so let's first run it successfully. So sig1 build test.
I mean, you can check that.
Sig with f deprecated, I guess.
Yeah,
blah, blah, blah.
and this is going to work fine because you've not added the annotation.
Yeah.
Okay. That's what we expected. We didn't expect any outputs. That's fine.
Yep. So here, then now it's deprecated. And honestly, deprecated doesn't even need anything more than this, because you might want to provide a reason, some context, where the thing moved to, whatever. But a comment does that already beautifully, since this code is supposed to
perfectly well.
Yeah, to be nuked anyway. Found deprecated code. So another way of doing this, okay, let's say that it's the function itself that's deprecated. So let's imagine, to be honest, most of the time you're going to be able to do this with a VRE exports, because that's the reality of it most of the time. But let's say that is this function itself that's deprecated. So I think we can do this, right? We haven't, I guess our deprecated right now expects to have an argument. So I guess I can pass void. We would have to implement this slightly differently.
Sure,
but yeah, this would also work, I would assume.
So that's going to emit an error, and you'll see why in a second. And by an error, I mean not the error you expect. Because you've passed void, the result of the expression is void.
Shit. Okay.
What you should pass is a void value.
A void value, yeah.
Yeah. And now, so that works fine. There you go.
That is not bad, honestly.
Yeah.
That is really versatile.
Do you want to extend your compiler development by having it allow you to not pass the void literal? Or
Let's go. Let's do it, okay. and then we call it a day. Like, we end with a bang. Okay, let me start. Let me start an incremental.
Sure.
Never hurts. Oh shit. Probably means we have deprecated stuff in our compiler. Okay, so we need to undeprecate our compiler.
Try that again. There you go.
Oh, I have it here.
You know what file we're going to be looking in?
Okay, so I guess we start from the definition. Oh, let me think for a moment. Let's. So we had AST gen, I think, where we mentioned this. Where do we define deprecated? No, not ZAR. There's another thing where we define the built-in. I forget what it is though.
It's the thing we're switching on here. Do you want me to just tell you what it's?
Oh, no, I can go to definition.
Okay. It's sure if you want.
Go to references. Oh, that one doesn't work. There we go.
There you go.
So parent count, I guess we can. How does this work? I guess null means variable number of parameters. Let's go.
Yep. So null, and that now means we're going to have to validate that ourselves, but that's fine. We can do that. So we're going to do that in AshGen.
Yeah, so we're not always going to have params 0, so we need to do params.
So I forget what the length is. Oh, I guess it's probably just params.len. So
yeah, it has
you
to
can
because
params.len. Oh yeah, you can do if.
0. What do we return? I guess we want to return a void value expression, right?
Yep. And because we're returning a 0ref, there's a for that. You can just return.
Return. Wait. Dot void value.
Yeah, exactly.
That's it.
Okay. Now we're not quite done yet because we've handled if there's 0 parameters, but because we've removed the parameter count, we could have like 2 parameters here. We don't want to silently ignore them.
Oh, you're right.
So this is why I was saying I would have done this as a switch on the parameters, but it doesn't really matter on the parameter len. But yeah. So yeah, you can say 0, return that. Ooh. Can Loris use a keyboard? Yeah. And then we can do else. We're going to want to error. So remember in SEMA, we errored using a function called fail. It's analogous here. So there is a function called, it's not quite called fail, but I think you will want fail node. Yeah.
Is the ASTgen fail node?
You probably got an ASTgen in scope already. It's probably aliased.
Yeah.
Yep, cool.
Fail node, was it?
Yeah. So that's just the kind of source location we're providing. In this case, we're providing a node. The normal way of wording this would be expected 0 or 1 arguments found, like whatever.
Do you put numbers or letters for 0 and 1?
I would do you do numbers. Yeah.
Okay, 0, 1 argument.
Yep, perfect. Oh, well, you're not returning fail node there. You'll want to return that otherwise. Yeah. I mean, yeah. Well, you can see the error in your incremental thing at the bottom.
Yeah, error set is ignored. Do we return? We try.
Just return this. We propagate an error up the stack. I know someone earlier was asking how the errors work, so I can explain that after we've done this exciting little bit of stuff.
Okay.
There you go. That works.
So we're good.
So
yeah, that's
now
a good point.
You're able to build a compiler.
What did you make me do earlier? Dforce?
Dforce link libc.
Will error ever be exposed for static analysis, linting, etc.?
Maybe. We're going to deal with that down the line. There is definitely value to it, but currently error is just not stable enough for that to be a good idea. Oh, wow, is the compiler built already? I forget how fast it is sometimes.
Yeah, yeah, so we go in here and we do add deprecated.
There you go. Oh, this is because you need to clear your cache.
Right.
Or is it? Wait, is it? Yes, I don't know. We'll see. I actually don't think it is that. It looked like it was breaking in. Yes, it's not that.
Oh, shit. What did we do wrong? Let's see. ASTRL annotated. Oh, we forgot that thing also.
Yeah,
oh, you know what? I think also print ZIR has the same problem.
You think what? Sorry?
I was wondering if print ZIR would have the same problem, but no, because print ZIR knows the metadata. Yeah, okay.
Yeah. So yeah, we're going to have to quickly change ASTRL annotate. And I will just tell you what to do with this one because you don't need to understand this pass too much. So if args.len is greater than equal to 1, you can do what you're doing there.
Oh my god. Okay, greater than equal to 1. Okay.
And you can do that, otherwise just return false, basically.
How do I want to do this one? Blocks? I think I want blocks. Okay.
Yeah. Okay. So now if you build the compiler, that should, I think, work.
God damn it. What about it in the comment as the second argument? You all want more complicated stuff, but what is the point? Who cares? Go read the source code. Go read the source code.
Get an error saying something's deprecated. Go and look at it. See why it's
never hurts. Yeah, it's always it always does good for you. Oh my god. Okay.
So now I expect this to work. Because obviously I knew the bug before. I was just testing you. Clearly, definitely. Yeah.
No, I think we didn't touch anything else. So
yeah, this should be.
There we go.
Okay, there we go. Deprecated code. And what you should do is you should try calling deprecated with like more than one argument and double check that it's erroring.
Fair point.
So I expect to see this error like immediately, pretty or not. Okay, because sure. Yeah. Oh yeah, I guess it wouldn't be immediate, but yeah, it's AshCheck would also show this because it's an AshGen level error, right? So obviously not on test.zig. You'd have to run it on the because AshCheck is on just a per file.
It's a
basis.
file. Oh, single file. So yeah, you're right. Obviously.
/thread.
Was it thread.zig? Yeah.
Yep. There you go. Cool.
Perfect.
You've done it. You've implemented your new favorite built-in. Do you feel proud?
Honestly, it's not bad. I feel like we could have chosen much worse things to try and implement just for fun. This one is actually kind of compelling. I like it.
Yeah, that's fair.
It's small, simple. It doesn't do much or past what it's supposed to do. I like also the fact that it integrates with a CLI argument. We also got the opportunity to see how that interacts with caching. How CLI arguments interact with caching in Zig is like it's very interesting. It's very cool stuff. Like it's also like if you ever happen to implement a similar system, it's a good example of how to make this kind of stuff work.
Right. Now, I think Loris is probably going to be desperate for dinner soon. However, first, I know people had a couple of questions aimed at me about compiler things.
Yeah.
So are you able to actually, if I share my screen again, can you throw that back up and I can...
Yes, I might need a couple seconds, but that's it.
Yep. Allow the... And I still want to see your screen. Okay, cool. So I know that earlier someone was asking about how error handling works, or like error reporting in the compiler. So let's take a look at SEMA. Let's look at the fail function. So actually this one is just a wrapper around this, because if you're having like notes on your error, then you have to do a bit more work. But fail with owned error message is, I don't know what I did there. Fail with owned error message is here, and this is the main function that's handling stuff. You can ignore this. This is just like a debug feature that we didn't end up using today at all. And you can ignore this. This is just adding, when you're doing stuff at comp time, you'll get like error foo, and then you get like note called from here. You might have a few of those. This is just the loop that's adding those notes.
Mm-hmm.
This is to do with the reference trace. This is, oh god, that's terrible. That explains so much. Sorry, I've just found a bug. Okay, what we do then is we have this error message thing, which we can look at in a second, and we put it into this failed analysis thing. This is an array hash map, plain and simple. And yeah, if this shouldn't actually ever be possible, I should change this to an assertion, really. But we put it into failed analysis, store it to the pointer there, and we also put it into this thing SEMA.error. Now that's actually not hugely important. This field basically exists because sometimes when we're unwinding the stack, there are things that want to throw their own notes onto the error. So, for instance, it might say, oh, this happened while we were analyzing this field, or while we were, I can't think of another example, but stuff like that. That's the only reason that field really exists. It's not actually necessary. The point is, this error is now kind of owned by this hash map. And then what we do is we turn this error.analysis fail. So not having error payloads, because I know that's what was mentioned, what this was mentioned in the context of, not having error payloads, it's fine, because we're storing the error out of band. The error.analysis fail is just there for control flow. And that's because we use try everywhere, or almost everywhere, that's kind of just unwinding the stack up until the point where we want to handle that error. There are a few places where we are going to do a little bit of handling of that error just to deal with something. So for instance, well, this is an example I was mentioning where we want to throw a little note onto it while we're unwinding the stack. So that's exactly what we're doing here. But we see analysis fail, then if we have a bit of context we need to add, we'll throw a note onto it saying that. Here, analysis fail here means that something in the standard.built-in is broken, and that shouldn't happen, so we just panic. Another thing where we're changing the error message, and that's pretty much going to be most of the handling in this file. Are there any interesting ones? There aren't many, so I'm just going to quickly... okay, there's like one interesting one, but it's a bit weird. I'm going to ignore it. But eventually, we're going to reach something like... this. So this is the code that's going to be semantically analyzing like a global comp time declaration, like when you write this at top level or inside a type definition. So if the code you have in here emits a compile error, then this here is going to put it inside that failed analysis map. We're going to return this. It's going to bubble all the way up the stack, right up to here. And then when we reach here, we say, well, if there isn't an entry in failed analysis, then actually this error came from somewhere else. So this error will have come not because we have directly errored, but because we referenced a different bit of code that errored. And so there's already an error message there, but we have just kind of silently failed. We've got a transitive failure, so we can mark that here, and we can forward the error more. And there will be points where this, like the call site to this function here, will basically just ignore that error in this case. That would be in compilation, ensure comp time unit up to date. You can see we store it in maybe error, and we just kind of silently drop this error here. So the point of the error is not to communicate all of the error state. It's just to deal with the control flow that arises from the error happening. Actually storing the kind of diagnostic information happens separately. And this is good because it keeps errors really lightweight, and it makes it easier to deal with memory management of this, because, for instance, we don't have to say, oh, like, if we had like error unions where errors could have values attached, then we need to say, well, what allocator is that inside? Who's responsible for deinitializing it? While obviously those same question marks exist here, it's much easier to define the answers. Because here we say, well, we've put it in this map. This map now owns that memory. And this map is responsible for cleaning up that memory when it needs to. So it's just a lot simpler and cleaner. And it means that we don't have like big error values that we're potentially having to reserve space for on the stack and clean up. It works a lot better in practice than error payloads would. That was a bit rambling, but I hope it answered that question. Were there other questions about compiler stuff?
I think this one was the big one. I don't. I don't remember any other particular question. Let's see if there was any new one.
Chat has something, feel free to ask. But very soon, Loris is going to cry because he's not had any food.
Can you change the switch to an expression and return from the switch? Yes, you can. We didn't do it, but you can totally. If you do that, if you want. So yeah, I think this is it. That was an adventure.
Yeah, I think this went lovely.
Yeah, we did a lot of stuff today. That was awesome. So, shall we call it a day? Is it time? Yeah. So let me see if there's anybody that we should rate. Like, has anybody been streaming today? I don't see anybody announcing their stream in Discord. Let me double check on Twitch who's live right now.
Running Zig, apparently.
Malky is streaming. Is he doing Zig? He is doing Zig. You know what? Let's rate Malky then. If he's doing Zig, go teach him Zig. Don't teach him about deprecated. This is not real Zig. We just did it in this stream, okay? So don't bamboozle him. But yeah, go watch some. Go help him learn great Zig. Why does he not show up? Wait, can you not raid him? Really?
Oh, does he have raids off?
He might, because I don't see him in the list. Wait, am I like typing? Oh no, you know what? I was typing his name real hard. That's the problem.
There we go.
Yeah, so if he's doing, I think he's doing the text editor in 1,000 lines book. So he has C examples and he needs to translate those to Zig. So he will probably need help because last I saw him, he was doing like Ziglings, and there's a bit of a jump between doing Ziglings, not knowing how to allocate memory manually, and then having to translate C code to Zig. So yeah,